provide half of its gross inland energy consumption. For instance, in 2013, we produced only 47% of our needs. As a result, the EU is dependent on non-renewable imports and primarily of fossil fuels. In the middle of the 2010s, the International Energy Agency was even predicting that Europe's energy import dependence would increase to 90% by 2035. And moreover, of course, in terms of environment, our energy systems and industry account for at least two-thirds of the total green gas house emissions. So it is therefore not surprising that the EU has set ambitious goals to change that. We are seeking to reduce our green gas house emissions by 55% in 2030 and to be climate neutral by 2050. The objective is to limit global warming to a manageable 2 degrees Celsius so that we can have safe, healthy lives and continuing livelihoods and stable, rich ecosystems. One of the keys to get there is to decarbonize our energy system and our industry by incentivizing energy use reduction and efficiency, primarily through innovation. Ultimately, we want to reduce our energy dependence, tackle climate change, and develop our economies with more jobs and industrial competitiveness. But well, you know, the task is daunting. But I have good news. If we look at the recent past, these targets were not empty talk. Until 2014, cumulatively, the EU and its member states had already invested 7 billion euros in research and development in renewable energies. Between 2015 and 2018 alone, the EU's research and development investment in the energy sector grew 24%. And in 2018, the total invested amount by private and public actors was 28.7 billion euros. As a consequence, employment in the renewables and energy efficient sectors in the EU grew 13% between 2010 and 2015. And in 2016, 55% of newly installed energy capacity was in renewables, and this is even excluding large-scale hydropower. And more. Europe has been over-delivering on its climate targets over the last 20 years. After signing the Kyoto Protocol in 1997, it reduced its greenhouse gas emissions by 18% in 2012 when the target was 8%. Then in 2007, the European Commission set a target to reduce emissions by a further 20% by 2020, but by 2018, it had already passed that milestone. However, there is still much to be done, as we know. If anything, climate change keeps worsening, energy dependency is still an issue, and stable societies where humans can flourish are at risk. This is why we have the European Green Deal, and this is why we are here today. It is in this context of ambition, innovation, energy efficiency that the soWhat project provided a potential answer to our energy challenges. You cannot be more relevant in the current international context. And what I find innovative here is the community approach of the project, understanding the untapped energy resources we have in certain areas and pulling them together to create local resilience, decrease impact on the environment, and create a basis for a just transition. And in order to truly highlight the achievements of the project, I would like to propose to you, the project stakeholders, that during the event, you try to answer these 4 questions. How did the soWhat project contribute to reduce energy use from carbon sources at community scale? What were the environmental benefits for the communities involved? To what extent did it increase the competitiveness of the industries involved? And in what ways is it an example of research and development supporting the energy transition? The answers that you provide here today, the outcomes of the project, are useful for us all going forward, not only for the local communities, but also for future research at European scale. So I want to briefly conclude just to give you a few words about our new partnership for energy-intensive industries at European scale under Horizon Europe, which is called Processes for Planet. This is giving continuity to the work done under Spire, of which the soWhat project was also a part of. This new partnership stretches for a period of 7 years and is placed in Cluster 4 for digital industry and space. The European Commission pledged 1.3 billion euros in funds, which is actually 27% more than for Spire. This amount will be matched by another 1.3 billion euro of investments from the process industry itself. So in order to meet these expectations, we have put forward a very ambitious strategic research and innovation agenda with 36 actionable innovation programs and a methodology for first deployments of technology and processes. Our main goals are to improve prosperity for all through a climate neutral, zero waste, and globally competitive European process industry. And just before I close, I want to give you an idea of the energy-related topics that the Processes for Planet calls under Horizon Europe are addressing. So these are examples from 21-22, and the work program actually for 23-24 it was about to be released at the end of November, so keep an eye out for that. So this concludes my opening. If you're interested in the partnership, feel free to contact me or check our website. You can become a member and help us achieve these ambitious targets of the European Green Deal and hopefully create a sustainable, happy society for all of us. Thank you.
Indeed, thank you very much, Bruno. I would like to pass the microphone now to Sarah Abd Allah. You have the floor. Speak.
Yes. Can you hear me? I don't think so. Yes? Okay. Good morning, everyone. Thank you for being here and thank you for joining this hybrid final event for the soWhat project. I'm Sarah Abdallah of RINA Consulting. I'm a senior researcher and I'll have the pleasure to walk you through the introduction or let's say a very short summary of all the experience that we have had during the past 3 years and a half. In particular, the soWhat project was, we launched the soWhat project in June 2019. And we've had this 3 years and a half of collaboration with all the partners with the aim to develop and demonstrate a tool to support industries and energy utilities in auditing and mapping their energy processes. In particular, the soWhat tool allows to compare and simulate different and alternatives waste heat and cold solutions. The tool supports actually in identifying economically viable scenarios where waste heat and cold and renewable energy sources cooperate to match the local demand. This project lasted around 3 years and a half, and since we are in this final event, as you can imagine, we are closing our activities by next week. I would say, so end of November. The methodology of the soWhat project relies mainly on 5 pillars. First of all, we had to develop and validate the soWhat tool. So it was one of the main outcomes. Secondly, we had to lead a research activity or research collaboration in order to develop the algorithm to integrate the waste heat and cold potential analysis into the tool. Then we had to analyze how we can unlock the potential for industrial use of this tool and to validate the tool with the involvement of industrial stakeholders and industrial stakeholders engagement, and then finally disseminate and prepare this tool for future commercial use. I would highlight that the soWhat tool is a commercial product that has been elaborated during the last 3 years and a half. So this tool was this project was actually had seen the participation of a large number of partners. We are talking about 20 partners, 11 demo sites from 6 countries. We are talking about lighthouses from Spain, Sweden, Portugal, Belgium, Romania, and Italy. And with the other 6 replication sites as well, to follow up the path that was designed during the soWhat project. And just to remind, as a reminder, the soWhat tool targeted audience it's the industries and energy utilities. The consortium itself to elaborate this tool is an industry-driven consortium. So we had to involve the industries in order to be able to listen and to integrate their needs into the soWhat tool. As I was mentioning, we have 11 demo sites in the project. This was quite challenging, actually, because 11 demo sites from different sectors in 6 nations, in 6 different countries. They are all reported in this table. It seems too, let's say, synthetic or too easy to summarize all these 11 demo sites with 11 different experiences in just one slide and one table. But let's try to describe them, maybe starting from the sectors and the country. We have, as part of the consortium, Lipor from Portugal and focused on the energy, waste-to-energy sector, Umicore and ISVAG and Imeris from Belgium, Göteborg and Weirberg from Sweden, MPI from the UK, Martini Rossi, Pessione Distillery from Italy, Petromida Refinery and Constanza District Heating Network from Romania. But let's get back to the tool itself. While the creation or the final result of the soWhat project, this tool is an integrated tool, and it's supported by an online workflow. In this slide, you can see how there is 3 aspects of this tool. The tool can offer an online, has an online free version, and then which gives the industries and the energy utilities, let's say, a taste of what the soWhat tool can provide. In the online free version, there are several aspects that are fully estimated and others that are partially estimated. In terms of partially, we can provide this actually in the advanced commercial full version. So we have elaborated this step-by-step accessibility path for the industries and the energy utilities. As you can see, the tool starts by estimating the baseline in terms of waste, heat and cooling, industry and community. Then we have the industries and the final user has the opportunity to simulate different technologies and the scenarios. And afterwards, there is this let's say, outcome of the tool that shows how reporting and that supports the reporting and the decision making. The targeted final user are industries, so main players of the sector, the municipalities, And regional energy agencies, public authorities that are the decision makers actually in that field. And finally, as well, the ESCO and the district heating network, because we are talking about this waste heat and cold, let's say, the recovering the waste heat and cold that could happen either internally in a site, industrial site, or externally. In that case, ESCOs and district heating operators are highly encouraged to consider all the opportunities in the surroundings. This was my first, let's say, couple of words to introduce the soWhat project. Thank you very much. I would like, before leaving the floor, to thank in particular my colleagues from RINA Consulting, Arianna Amati and Francesco Peccianti, who are actually the coordinators, previously Francesco and afterwards Arianna, that allowed the smooth operation or smooth development of this project in the past 3 years and a half. Thank you very much.
Thank you very much, Sarah. Thank you very much, Sarah. The next speaker is an associate professor at the University of Birmingham and soWhat's very own responsible for industrial sites assessment and technology database. Mr. Adriano Sciacovelli, you have the floor.
I'll take the podium just as a matter of comfort in a way. Cheers, thank you. Okay, excellent. Is this my presentation already? Okay, brilliant, fantastic. Thank you very much for the introduction. It's my pleasure to give a snapshot of this important phase of the project, the Industrial Site Assessment and Technology Database, which basically covered the first, let's say, half or one of the first work packages of the project. I was particularly glad to lead this piece of work, but I have to obviously acknowledge some key contributions that fed into what I'm going to present here. Obviously, people in my team in Birmingham, but partners here were instrumental to the work that we perform and that the result that we achieve. Obviously, IES team, the RINA team, MPI, and in general, obviously, the industrial partners for the support in the industrial site assessment and technology database. So I would like to just give first an overview of where I want to go with this presentation and then guide you a little bit of where, let's say, the main value of this part of the work is. So there are three, basically, aspects I will cover. Obviously, the industrial assessment, the keyword that has been done around technologies that allows recovery and utilization of waste heat. A subsection of this one would be a part on storage, which is one of the, let's say, novel elements that was put into the project. And obviously, happy to take questions eventually if there is time or during the coffee breaks as well. So for you to appreciate in a way what has been done in the first phase of the project, I need to build a quick mental model about why soWhat tool is so relevant and what is intended to do, and to map these pillars onto the presentation as well. So first of all, obviously, we are working on industrial decarbonization, so industrial sites where there might be amount of heat, process heat, or in general heat that is generated but not utilized. Okay, so let's call this waste heat. Interestingly enough, there is potential for also waste cold, where refrigeration and cooling might be produced for internal uses, but a certain amount is not utilized and it's in principle wasted. So from technical standpoints, the second part of the mental model that I'm trying to build with you is that this excess waste heat to be recovered somehow requires some form of technology. And in the project, we have looked at three basically macro areas or macro categories of technologies. Reutilization, where the heat is, let's say, captured and reused as it is. Technology for waste heat and cold upgrade. This means that heat is somehow converted, its temperature is changed, let's say it's raised, typical example here are heat pumps, and potentially, third category, the heat or the cold is converted in different form, like in cooling or in electricity. So once we have, let's say, the asset to recover the waste heat, what we can do, and what the soWhat tool helps to understand, is how to reuse this heat either internally into the industrial sites, or potentially, and this is one of the key, let's say, selling point of the soWhat work and tool, externally. So we might interface this recovered heat with external network, basically. This can be district heating, so for industrial symbiosis between industrial site and eventually the, let's say, surroundings, and if heat is converted in electricity, perhaps with electricity and energy networks. And on top of that, if we have, let's say, increased amount of renewables and intermittent sources, we might want to store some of this energy to basically use it at the best time. So out of this, let's say, quick run through the basics of waste heat recovery, you might understand that there are 3 key pillars that were, let's say, part of the work done in this phase of the project. Understanding the energy flow, so actually identify how much waste heat is available, have the right information to do this assessment, so data from industrial sites and in general from the infrastructure that you see here, and obviously the technologies. And I'm going to touch upon each one of these 3 aspects that were indeed covered during this industrial site assessment and technology database. So let me perhaps just quick mention what ultimately we achieve in this phase. So obviously those 11 demo sites that were mentioned before were assessed, and the, let's say, amount of waste heat and potential for recovery identified. A number of technologies were analyzed, approximately 40, and associated algorithms developed, so that they are now integrated in the soWhat tool, so those technologies can be simulated and their behavior performance in recovering heat actually computed. Similar also for the storage technology that I mentioned before. Very importantly, big chunk of work was done on understanding how to overall, let's say, overcome the challenges in collecting data from industrial sites necessary for this type of assessment, and also some work on the mapping algorithms that I'll discuss briefly as well. So going back to this model, I'll touch upon, therefore, on those 3 key aspects, starting from basically the industrial sites and the assessment that was carried out in this area, in this space, with the demo site in this project. So the assessment was done, and let's say the right strategy to do it was also identified during the project, and was done in 2, let's say, subsequent steps. First, at sectorial level, so what, let's say, work and actually public available deliverables that we believe are quite, let's say, valuable for the community, led to identify how much of this resource is available at sectorial level. So you see here one of the, let's say, key or snapshot of the key results from one of the publicly available deliverables, which I recommend to obviously access and have a look, where work from, and this particularly from RENA team and MPI team, was quite instrumental in essentially identify how much of this waste heat is available in each of the key sectors across Europe. So what you see here is a comparison between the overall energy consumption in a certain sector, how much of that is in the form of heat, and then how much is estimated to be wasted. So what soWhat tool helps to is to basically remove the 3rd bar in this graph and turn it in either, let's say, the red one or the bluish one. So the gray bar is an inefficiency here that soWhat tool helps to essentially remove from industrial industries. So obviously, not necessarily all that amount of heat can be recovered, and the work that was done identified that it's a certain fraction of it is actually technically recoverable. The work was also exploring different methods to do this assessment. So for increasing the robustness of the results, the, let's say, assessment of how much waste heat and coal was recoverable was performed in 2 slightly different ways, but you see that by and large there is a reasonable coherence between the methods used. But the key message here is that there is terawatt-hour of waste heat and coal wasted at each sector on a yearly basis. That obviously needs to be addressed. So this is fine as long as we are working at sector level, but we want to help industrial partners, industrial sites, and the soWhat tool intends to do that. So we have to drill down at more granular level and move from a sector to actually process level. so that the industrial players can actually identify how to remove these inefficiencies. So you've already heard about the industrial sites. I want to just perhaps add a couple of things about, obviously, why we have these great partners, or we have these great partners on board. I'll just want to draw the attention to the last column here. So you notice a wide range of temperatures. This is typical temperature of the heat used, or either used or wasted in these processes. So this range of industrial sites allowed the project to test the tool in very different conditions, and also essentially identify way to recover waste heat from very low, let's say relatively low temperature heat, 70 degrees or so, to particularly high temperatures across the sector. So for example, the food and beverages are typically relatively low temperature waste heat, and if we move to a steel and metallic processing of metal manufacturing, obviously we are going above 1,000 degrees C, and it's essential that the tool allows to basically span all these range of temperatures. So as I mentioned, the first phase looked at, obviously looking at assessing at process level, at individual site level, how the waste heat was wasted indeed. And this has been much more, let's say, challenging, but also basically the added value that this tool will help. So as we move to assessing the industrial sites, we found that in general, it was consensus in finding that at industrial scale, first is essential to quantify where this waste heat is occurring. So literally at which location in the process, which are the units where heat is wasted. And this hinges on having a significant amount of data and information about these industries. And the soWhat tool has an embedded feature or set of features to actually allows the user to capture the right amount of data. And these slides just give you a sense of what is needed. We are talking about really the pattern in energy consumption, the process flow diagram, so actually the layout of the industry, and the perhaps, let's say, flows of products, masses, etc., and eventually also the way that, let's say, occupants uses the buildings of the industry. And overall, out of this initial let's say, assessment of industrial sites, a step procedure to capture data was identified, and soWhat tool has essentially a guided procedure along 6 macro steps that allows the end users to obtain the right data to identify the amount of waste heat, and then to select best decisions to valorize this waste heat. So this was one of the key aspects in the first phase of this industrial assessment at industrial scale. So obviously we done, and the team of the project did this for all the industrial sites, all those 11 sites that were presented before and that I briefly touch upon. So obviously there is no time to go through all of them. I picked, let's say, an exemplar case to give you a sense about the potential and the capabilities of the tool, and obviously of the assessment that was done. So I picked the industrial, let's say, demo site in the United Kingdom from Material Process Institute, which is basically in the steel manufacturing sector. So it's a relatively large pilot plant with electric furnaces and casting at ton scale potentially, where, let's say, the tool was used to, or let's say the assessment was carried out. You see on the left-hand side, let's say a typical, let's say, flow diagram of this sector. Just, let's say, to give you a sense of how this assessment looked like, with the information that was emerging from this work, what you see here is a Sankey diagram that shows what the industrial assessment led to. So what you see from the left-hand side, basically, are the, let's say, primary energy sources used in these processes, and each branch of the Sankey diagram essentially identifies how those primary energy sources are used in this processes or individual units into the industrial process. So ultimately, at the very right end, we can identify what was the use of the energy that was, let's say, consumed, and eventually if there are sources of waste heat. So these gives, let's say, the industrial partners, as well as potentially the user of the soWhat tool, a capability to see visually how much the inefficiencies are, or the waste heat is, and quantified. So the size of these branches is basically proportional to the amount of energy flow. And in this specific case, the assessment led to identify that there was significant amount of waste heat in a particular form, in hot solid steel products. So products that are, let's say, casted, they are quite high temperature, they have to be cooled down, and in cooling down, this heat is wasted from these solid products, and that would be a source of waste heat that could be potentially valorized, as long as there is, let's say, a technically feasible way to do it. And this type of work in the industrial assessment was done and replicated for all the industrial sites that I mentioned before. So going back to our simplified model of waste heat and cold recovery, I'll move to the second pillar that was covered in this part of the project, which is the technologies. The actual assets that allows to recover and utilize this waste heat. And this is one of the work that the University of Birmingham, piece of work the University of Birmingham led. And we have looked at one of the, let's say, key selling points of the soWhat tool is that it spans across all the possible type of technologies that are available on the market or that are emerging. So this, an interesting bit is that the soWhat tool allows potentially the end users to also be conscious and aware of emerging technologies so they can direct their investment at the right time so that they can basically have a competitive advantage by adopting more, let's say, more advanced technologies. But there are essentially five categories from traditional ones like heat exchangers, waste heat to cold, so sorption chiller, for example, heat upgrade, heat pump in general, and potential power cycles, where the waste heat is used to produce electricity. And the remaining one, which I will discuss separately, is on energy storage and thermal energy storage. That is enabling technologies, as I will discuss later. Let's say a good amount of information is captured in one, again, of the public deliverable of the project that is on the website, where, for those of you that are interested, you can read 250 more pages about technologies. Obviously, I cannot cover all of those. I'm going to give you, again, an exemplar case to give you a sense about the information that is there and how it can be benefit to you. So, as I mentioned, two macro areas were covered in terms of technologies, established one and emerging one. So I'll pick just one, established one, to give you a sense of the information in that deliverable, as well as basically in the database that is embedded now in the soWhat tool. So typically, this is, let's say, a condensing heat exchanger technology. In the deliverable and in the soWhat tool, you have an information about the typical type of application. So what you see on the top left is a typical use of these technologies, is to recover relatively low-grade waste heat by condensing flue gases. The work or the deliverable provides also, let's say, the key information about who are the suppliers of this technology, and very importantly, for industrial players to do technical assessment, and for obviously the soWhat tool algorithms as well, there is technical and economic data about these technologies. So you can find essentially performance indicators, efficiency, let's say, and costs of these specific technologies to basically take informed decisions on investing potentially them or using them. So just to give you a sense, obviously the same was done also for the emerging technologies. I pick another one from a different class. This technology belongs to the heat to power technology. So it's a power cycle. What it does, it converts basically waste heat into electricity. So what you see there in red box is where the waste heat is captured. This waste heat is fed into a thermodynamic cycle that uses, in this case, supercritical CO2, and basically the cycle produces electrical power. So it recovers waste heat by converting it into electricity. And there are various reasons why, let's say, supercritical CO2 can be used and why it's beneficial. That's part of the information captured in this project. As I mentioned, this is an case of emerging technology, so there is, in the work done, some sense about how we compare and contrast to traditional ones. So here what you see is the small one is a supercritical CO2 technology for recovering waste heat, and the big one is the counterpart that is currently used. So you see where is the benefit. It's kind of 10 times smaller, much more compact, smaller footprint, and potentially easier to install. And similar, there is some indication in this case about the TRL level, so how close this technology is to be adopted, and what are the typical performance parameters for this technology, so that eventually industrial stakeholders can be aware of the fact that this is coming up and is near to market potentially, and they can take actions if necessary or if the technology fits their needs with the with the support of the soWhat tool. Okay, moving to the last pillar that I want to cover with our mental model here for waste heat recovery. So let's say one of the key aspects also of the soWhat tool, where we wanted to look at also how energy storage might fit into the picture of waste heat and cold recovery valorization. So the fundamental reason is the following one. Traditionally, let's say industrial processes have obviously used, let's say, mostly fossil fuels as a way to produce process heat or cooling. So a dispatchable form of energy. This means that you can always potentially use fossil fuel at any point in time. That dramatically changes if we move to intermittent renewables or perhaps intermittent waste heat, where the primary source, let's say the waste heat or eventually the renewables, might not be necessarily available when we want to use it. So we need an extra degree of freedom in the middle that allows to either store, let's say, the primary source when it's not used, or release it when we actually want to use it, but the primary source is not needed. So the work that was done was about thermal storage. There are a number of also open access publications that were produced in this project that are, again, available for consultation, and obviously the necessary algorithms and characteristics have been brought into the soWhat tool as well. So I'll give you a snapshot about what has emerged from this part of the work in this project. So first of all, there is a range of possible technologies. So most of the industrial players, we become aware that they are aware about traditional way to store heat or thermal energy, let's say in stratified hot water tanks, up to 150 degrees C if you work in pressurized conditions. But there is a massive range of emerging technologies that are belonging to different categories. So there are basically three classes of technology that can store heat by either, let's say, processing material, for example, by melting and solidifying certain substances, or using reversible reactions. And going back to the potential question that was asked by, or point of discussion of the first presenter, how this work has also had extra benefit beyond the project itself. And I'll give you one personal perspective from the University of Birmingham. Out of the understanding that we developed in this project, we actually developed one thermal storage technology that uses a certain substance to store heat at 100, 200 degrees C. And this is now in use in an industrial partner in a national project. But without the support, without the understanding developing the soWhat tool, we couldn't really develop these technologies, and now it's used in a basically food and beverage industry that allows to basically mitigate the intermittency of waste heat and make the process more efficient. So, as I mentioned, there are various applications from energy storage perspective. The typical one are energy efficiencies, so waste heat recovery, valorization, etc. But as I mentioned, basically also quite a bit of renewable integration can be facilitated with energy storage. And again, the algorithm and the assessment that were carried out in this phase of the project fed into the development of the tool that you will hear about later on, so that the tool allows to take also decision not only about those previous waste heat and recovery technologies, but also on energy storage. And that's, again, we believe to be an added value of the project and of the tool overall. So I'll give you just an example again of benefits from an industrial perspective of using this thinking, this tool, and in this case using thermal storage technology. We have developed, let's say, a specialized methodology in this phase of the project to help industrial players in deciding which is the best thermal storage technologies for their case, how to operate it, and therefore ultimately how to select it and how this benefits the industrial players. So just give you again one example here. This is an example of coupling thermal storage with another waste heat recovery technology. So you see here on the left-hand side an industrial, let's say, site. This case was steel industry, where we consider to have thermal storage to make basically intermittent waste heat more easily usable. So what you see on the right-hand side, beside, let's say, the technicalities, is a profile in time of the intermittency in waste heat from that industrial site. So with storage, we basically mitigated that intermittency so that it could be used more easily by what is called their power block Power block is a technology that converts that waste heat into electricity, but without firstly basically make it more smooth and more constant. With the thermal storage, this was not particularly possible. So obviously, economics matter. What you see on the right-hand side is the amount of electricity that was produced out of waste heat. And on the, let's say, horizontal axis, you see different type of storage technologies. So basically, you see that more electricity can be produced with certain type of storage, which means that ultimately, if the industrial players either reuses that electricity for their own needs or potentially sell it to the grid, if, let's say, regulatory conditions allows, their economic case improves, essentially by either producing energy for external use or for reducing their own internal utilization. So, yeah, this brings me to the last slide. Quick final run-through about the contributions of this phase of the project. So provide a full waste heat and coal assessment at EU level for each main industrial sector. Assessed 11 industrial demo sites. Contributed to basically obtain a clear and a systematic procedure to capture data necessary for assessing waste heat and waste coal recovery strategies at industrial level. We develop a range of, let's say, algorithms and understanding of technology that is now embedded in the soWhat tool. And ultimately, again, on the R&D aspect, particularly advance the understanding and the utilization of also energy storage in the context of waste heat recovery and renewable utilization in industrial sites. So I'll spend the last 25 seconds to thank, obviously, all the partners here, all those that worked in team at Birmingham and coordinators, and you know who you are, that feeds into this great work, and it's been a pleasure, and I'm very, very happy that we succeed in completing this piece of work, and thank you very much for your attention.
Great job, Adriano. Thank you. Our next speaker is a research and project manager at IVL, and soWhat's responsible for the waste management business model analysis and Swedish demo sites. Madam Sofia Klugman.
Good morning. Do you hear me? Does it work? Perfect. So thank you for inviting us to Constanza. It's a pleasure to be here. I will now present some business model aspects for waste heat and coal valorization. Because as you heard, there's a great potential for waste heat use in the EU. It's about 25% of the heat demand in EU that could be covered by waste heat. Or 25% of the heat demand in the building sector could be covered by industrial waste heat. So it's a huge potential. And yeah, please, next slide. Oh, that's me. Where should I? The middle one. Yeah. So when you have found all this technical potential, what do you do? Why doesn't this happen already, that this potential is used? What we have looked at is the drivers and the barriers, and looked into different business model aspects to make it easier for this to be valorized. So to attain a viable business case, it's important to find a win-win case, of course, for all the partners in the collaboration, and to find a way to attract financing. And some aspects you need to look at to find a good business model is to look at business risks, the contractual arrangements, the cost and benefits, of course, and the ways to finance the investments. So, I mean, when you're talking about drivers, it's always frustrating to see a resource, a good resource, just go up in smoke. But if you look more into detail from this different stakeholders' perspective, you you can see that the costs also can be saved from when you do not need to buy fuel and electricity, of course. And there are also costs at the industries for active cooling, such as cooling towers, that you may not need when you can sell the heat to an external partner. And of course, you can replace fossil fuels, which reduce greenhouse gas emissions. And on a regional and national scale, there are further drivers, such as to reduce dependency on imported energy and also job creation, you can see. But now, the barriers, why isn't this already happening? Well, sometimes it has been, maybe historically, not now, a low cost for the current heat and cold. And it's also often a very high initial investment cost for piping and other technologies. And sometimes it's unclear with the policy what if it really promotes energy reuse. Because it's a lot of talk about renewable energy, but this is something, well, it's a bit unclear in the policy. And there's a lack of regulation sometimes in countries where there are not much piping for heat deliverable. Then maybe there's no existing permission process for piping. So that could be a barrier also. And in those countries, there is also a lack of technical know-how, of course. And a big thing is that stakeholders wish to be independent on others. And I think this is kind of the core part. What can actually make you trust someone else so much that a big part of your system is dependent on someone else. And from the energy company side, there's always a big risk for them if the industry is moving or closing, or maybe even just changing the processes so that they cannot generate heat anymore. Yeah. But what we see is that many of these barriers may be handled by contractual arrangements. So that is something we have dug into also, how to actually manage this, to overcome these barriers. And we have also identified the business risks. And this is something that is also elaborated in the tool. So a risk assessment can be made and some suggestions on how to mitigate risks. But as you know, there is no such thing as a risk-free investment. But depending on local prerequisites, the risks related to heat collaboration will be quite different. Especially a watershed is if there is an existing heat network or not. But you can also see this as a risk-reducing thing, because you will not be dependent as much on fuel and the fuel prices that fluctuates. So it's not only risks; it's also a way to reduce risks. As with the barriers, most of the risks can also be mitigated with good contracts. For example, you have to have a clear contract that states the responsibilities, which part of the technical equipment and so on is on which side, and who's responsible for, well, if the things doesn't work as it should, and how to also communicate those things. And one way to mitigate the risk of well, when there is no existing district heating network, and two partners that are not energy companies are to cooperate about excess heat, maybe between two industries, or as we have example in this project, an industry and an airport, for example. You can invite an ESCO company to do this, to help with the collaboration. That's one business model. And some aspects that are important to include in the contractual arrangements is, of course, the ownership and also maintenance of the different parts of the system, the technical system, and the pricing. How will you, over time, do the pricing of the heat or the cold? And responsibilities, well, like what happens if in case of failure of delivery, and how long will the contract period be? And we have, in this project, we have shown some examples of how this is solved in existing collaborations. Like a normal period of contract is 10 years, for example. And sometimes you can also include an exit paragraph. Like if an industry cannot, maybe they are changing the processes or so, then maybe they have to announce 2 years in advance, so that the energy company has a chance to replace that delivery. And the most important thing for the contracts is that the collaboration really is a win-win for all the stakeholders. So another example here from one example from Sweden. This is a normal common setup that the industry has a heat exchanger on its side, which it owns, but then the piping and the heat exchangers on the city side is owned by the energy company. And in this case, we had looked at, then they renegotiate the price every second year, and the contract period is 10 years. Yes. So also the reason why Sweden is here in this project is that we do already use a lot of waste heat for heating. About 9% of all the heat for district heating is from industries. And that is in addition to the combined heat and power plants, which also are common. So another example is when a privately owned commercial building wants to achieve a greener profile, and a privately owned industry wants to make use of their excess heat, but the energy is not core business for either of these partners. So they involve an energy company, an energy service company, which can provide services such as both the energy infrastructure and maybe power generation and energy supply, and the financing, not at least, and the risk management for the system. So when we also have looked into some financing schemes, there are often these collaborations are mixed public and private collaborations, and you can set up this in different ways. The business model could be through ESCO contracts, as I said, and you can have a concession that a company is awarded to own and operate the network until the end of that contract period. And you could have a leasing setup, and property differentiated by elements, like the example with the industry that owned the heat exchanger, for example. And also there are additional setups. And these examples are suggested in the soWhat tool also, as a starting point for discussions on what is the most relevant for the case you're looking at. And often there is available financing support from the European Union and national administration. So, and sometimes some tax advantages also when you use it. It's very different in different countries, but this is something we have looked into in the project. Yes, that was my presentation. Thank you
very much, Sofia. The last speaker of the panel is an R&D manager at Cartif and soWhat's impact manager. Please welcome Francisco Morentin.
Thank you very much. Do you hear me? Yes. Perfect, thank you. So, as Alexandro mentioned, my name is Francisco Morentin. I work from Cartif. I've been involved in the soWhat project from the very beginning of the project, and I'm going to try to make a short presentation of how to maximize the impact of waste heat. And I can already anticipate that I am going to overlap with my previous presenters, which is normal, because as you will see next, we consider there are three key aspects in waste heat recovery, and the three key aspects have been covered more detail in the previous technical activities. So, just to contextualize a little bit, I would like to start with the official waste heat and cold definition, and we have an official definition in the Renewable Energy Directive of the European Union, and it's important to read it. So it's unavoidable heat or cold generated as byproduct in first industrial, second power generation installations, or tertiary sectors, which would be dissipated and used in air or water without access to district heating or cooling system or so on. Okay, but the key point here is that the official definition of waste heat considers three possible sources: industrial, power generation installations, and tertiary sector. So this gives us to a classical classification of waste heat, okay? And waste heat can be classified in two types: conventional waste heat and unconventional waste heat. Conventional waste heat includes especially energy-intensive industries, paper, glass, cement foundries. Some of them are included as demonstration facilities in soWhat project, and also includes unconventional waste heat sources, which are, let's say, the new targets: data centers, tunnels, metro stations, and so on. In conventional waste heat, the waste heat is easy to be identified and usually already available at high temperature levels. In unconventional waste heat, it's not so easy to identify, and involved temperature levels are always lower. Important that in soWhat project we focus on conventional waste heat sources. So, I guess all of you are already familiarized with the fire triangle. The fire triangle tries to explain that to start a fire or to sustain a fire, you require three elements simultaneously. You require heat, oxygen, and fuel. So we are, from the very beginning of the project, we consider this, this concept to waste heat recovery. So we also use this analogy, let's say, to try to define the three simultaneous components required for waste heat recovery. And the first one is a source of waste heat, which has been deeply explained by Adriano's presentation. The second required component or element is a recovery technology, a recovery or a thermal storage technology. And the third element required is the end use of this recovered heat, of this recovered energy. So, starting with the waste heat sources, I'm not going to repeat Adriano's comment. You have plenty information in our website, but we consider what it is called the energy cycle. So from a conventional, and I repeat, conventional means industrial factory perspective, the energy is usually initially converted, and this conversion usually generates conversion losses, which can be a possible source of waste heat. For instance, typical example would be steam boilers that convert natural gas into steam. Then we have the distribution losses when this energy is distributed along the different industrial facilities. And again, this is it's a loss, but not usually considered a source of waste heat. And we will end with the end use of this energy, which again represents an opportunity, a possible source of waste heat. Regarding the different temperatures involved, quite quickly, from an industrial perspective, from a conventional classification of waste heat sources, you can find combustion exhaust, process of gases, waste steam, cooling water, and finally, ventilation systems. But in this case, ventilation systems could also be considered unconventional waste heat sources. Okay, again, you have plenty of technical information in our first work package deliverables in our website. So, again, exactly the same regarding the technologies. Adriano perfectly mentioned it, I'm not going to repeat it. So, we jump into the third element of the triangle, which is the end use of the recovered heat. And here we have two possible uses of the end of the recovered heat. We have internal use and external use. And I think we are forgetting sometimes internal use. Internal use of the waste heat in a factory, it's quite important. I mean, for every case we found with where a factory, sends the recovered heat to an external use, we can find tens of cases where this internal heat can be used internally within the factory premises. And I think it's important to not forget about that. Indeed, in between our demonstration cases in the soWhat project, we have two use cases where recovered waste heat has been, internally delivered without exiting the factory premises. So, when we talk about internal use of the recovered heat, we have one straightforward option, which is to recover and directly re-inject the possible waste heat into the same process that originally caused this waste heat. This is a typical example of retrofitting of boilers to install economizers and so on. Usually, it's not considered as a waste heat recovery process. Sometimes it's perceived by factory managers as an improvement of the machinery efficiencies. Then we have the second and more complex case, which is waste heat is recovered from one industrial process, and this recovered and transferred to a second manufacturing processes, but within the factory premises, within the boundaries of the factory itself. And sorry to repeat it, but this is two of the use cases we have. And jumping into the external use, then things get terribly complicated, as Sofia mentioned it, because we have a possible source of waste heat, a possible company, a possible actor, and we have a different actor which could be the user of this waste heat. And things here should be, you can initially think it's simple, but things get really, really complicated because, as mentioned, control arrangements can really, really, really get really complicated with or without the presence of ESCOs. So you may have a possible use case where, from the technical perspective, everything is clear, not problematic at all. But when you make the numbers, there's no possible economic arrangement that satisfies the economic requirements of all the partners involved. So, to summarize, we have 3 elements to consider simultaneously. Obviously, to maximize the the waste heat recovery globally, we will have to rely on external recovery, and this probably can only be made through district heating. There are several barriers to overcome, and again, it's important to consider the 3 aspects simultaneously. So, challenges for waste heat recovery can be typically classified in technical, economical and financial, legislative and regulatory, societal and cognitive. We have covered all these possible aspects in the lessons learned about the soWhat project, including legislative, including economics. I'm going to give just a short taste of 3 of them, the technical cases, and I'm going to consider three possible cases, which is temporal mismatch, location mismatch, and quality mismatch, okay? These are going to be general rules. It's important to remind that at the end, you require a specific study for each use case. That's why it's so important to have a tool like the soWhat tool that allows you to I would say, to do the first preliminary analysis, okay? So, but talking about temporal mismatch, it can be considered as first as an hourly or daily mismatch between the waste heat availability and the heat demand. But secondly, and most common, is the seasonal mismatching between the summer production, the summer minimum heat demand, and the usually flat production of waste heat. So possible solutions, also related with Adriano's presentation, are the introduction of district cooling and absorption chillers, the introduction of seasonal thermal storage, or considering heat-to-power systems if we are moving in the right temperature levels. Second mismatch possible is the location mismatch. Usually, sources of waste heat, large industries, are not usually near district heating networks. We go back to the previous Sofia's presentation. As he mentioned it, typically the biggest investments in piping affects all the profitability and economic feasibility of any waste heat recovery integrating district heatings. And even if you use long-term contracts or you simulate or implement a multiple suppliers and consumers use case, the general rule is that the biggest amount of energy you transfer, the lower economic cost in terms of euros per megawatt hour of thermal energy transfer. And finally, to end up with the last one, is the quality mismatch. So quality mismatch corresponds to several aspects. Typically, the first one and most common is different levels in the temperature level. So the waste heat source has a lower level than the required by the district heating network. But also there are other quality mismatch to be considered, like intermittent generation of waste heat, insufficient heat volume, presence of dust or corrosive elements in the waste heat streams that affects the lifespan, the useful life of the heat exchangers, and so on. So again, general possible solutions, but I remind it's important, it's mandatory to go case by case, is considering the reduction of the district heating temperature, and this is much easier to be said than to be done, because it's the typical consideration that is not usually possible in existing district heating networks, because you have to retrofit all the facilities. And the second one is the temperature lift through heat pumps. This, from the technical point, this is not so problematic using heat pumps. Indeed, the global trends go through this option. You only have to consider that you are including or incorporating an additional electricity consumption, which means an additional economic cost and some possible emission impacts. And that's all from my side. I would like to thank all my colleagues for their work during this period of the project, and that's all. Thank you very much.
Thank you very much, Francisco. If there are any questions that you have in the hall, this is the right time to address. Some of the speakers will not be with us in the afternoon. Are there any questions? If not, we are go for a coffee break, and we will meet each other here at 12 o'clock. Okay? Thank you. Good. 2. Probă, probă.
And then go to the next slide. It's just this one.
Welcome back. To continue, we will have with us Nick Pershouse, Senior Project Manager at IESVE and soWhat's Technical Coordinator. You have the floor.
Hello, everybody. It's a pleasure to be here. This is not the right slide.
I'll slide. Go forward, forward, forward.
This is going back to the start of today, so do I have to go through everything?
Yeah, unfortunately. It's like you're counting passengers. Just a little more.
So this is just a good recap on what we saw earlier, and also if people have been learning how to speed read,
Next one, next one.
this is a good way to do it.
This is not going to be so long. There you go.
I like the fire triangle. I like the Okay, back in the room. Right, so I'm just going to present to you the culmination of the software that we've implemented through the project. And we've taken all of the different I guess pieces of research that have been done earlier in the project that you saw earlier this morning. And this has actually now been implemented into an integrated piece of software. So I think one of the first presentations that we had talked about what the soWhat tool does. And it's important to remember that we actually have two key soWhat tools. One is a free tool that is available online, and if you go to the soWhat website, the soWhat project website, you will actually be able to access that piece of software for free. And the other tool is something that's much more advanced, and that is actually something that we intend to release commercially after the project. Both tools have a very similar I guess aim and objective, and what we're trying to do is enable people to try to understand and assess the waste heat potential and waste cooling potential that they might have in their community or in their own industrial facility. And we're also trying to enable any user to understand what they can actually then do with that waste heat or cooling. A lot of people ask me, why is the project called soWhat? Well, it's because the idea was we're trying to allow people to say, I have lots of waste heat and cooling, so what can I do with it right now? And that's what this software is aiming, allowing people to do. So we see on the left-hand side, it's about enabling easy data collection to understand your current situation. And then the column in the middle is really around simulation of different technologies that we heard about earlier. And then on the right-hand side, it's about allowing decision support and analysis for a variety of different users. And Sophia was talking about sort of business models and the financial aspect of things earlier. And that comes into this decision support. There's definitely been two key areas that we've focused on in the project. One is the technical element and how you can technically sort of do some of these technologies to recover waste heat and cooling. But the other aspect is how can this now be done financially as well? And there are two different types of audiences, two different types of users that want to know that kind of information. I think we've seen this slide earlier, but it was just about who are our actual users, who are we aiming this software at. We're looking at industry, where there may be any waste heat or cooling. We're also looking at municipalities and regional energy agencies, and we're also looking to engage sort of ESCOs and district heating operators as well throughout Europe. So what I'm going to do is just talk everybody through the steps that we have in the free tool. And I'll just show an example of that, and then I'll go through the more advanced tool. And all through this, the whole presentation, I'll be using the case study or the demo site that we have in Italy, just as an example as to how you can use the tool. So here, all the user needs to input to try and understand their waste heat potential is their country, the main fossil fuel that's used on their site, their industry, and the overall energy consumption of that particular site. And this then looks up against all of the information that we've been able to find about all industrial sectors and their waste heat and cooling potential in academic research. And we then run different calculations to come up then with the waste heat potential of that particular site. And here you see it gives you a number, 6.73 gigawatt hours per year of waste heat potential. And you can also see that split by different temperature grades. And obviously how much you'll get and how much percentage of that waste heat is by different temperature grades. I think it's important to remember as well that one of the things that we found in the project is there is actually no agreed definition of sort of temperature grades or way of standardizing the actual waste heat or cooling. And I think that's something that can come out of the project to recommend that the EU looks at that and tries to standardize it across different countries. So here we've just like pretty much split the temperature grades as best as we can. From there, you can actually try and understand what technologies are most suitable for that user to actually implement at their industry. What we've been able to do here is take all the, I think there's maybe about 35 different pieces of technology in terms of waste heat and cooling recovery, and we've mapped that to different temperatures and different industries to try and allow people to understand what's the most applicable technology for them to now look at in a bit further detail. And this also shows as well something around market maturity of different technologies. The project has tried to model not only technologies that are easily available across different countries in the market, but also ones that are just coming to market or are actually more just now in development phases. So if an industry wants to look at something that's quite innovative, this market maturity guide will also allow them to do that. Once you select your technology, so here it's selected as condensate heat recovery. We then get some figures around what that technology might be able to produce in terms of the final heat outcome, and also the maximum sort of temperature that it will give as well. And the next aspect of the free tool allows you to do a quick risk assessment for your particular industry, which starts to try and allow you to understand what the particular issues or risks might be for implementing that technology. And we can see there that there's a sort of spidergram that actually shows the different elements of risk, and then that allows an individual to go away and try and think about, okay, is this worth doing or not? How can we mitigate those risks? We've also implemented in the free tool quite a simple financial analysis to give somebody a quick understanding from just inputting different costs and investment scenarios and sort of discount rates over time, what their payback or internal rate of return or net present value might be for that particular investment. And I should stress that the overall aim of this free tool is to allow somebody just to get a quick guide as to, I guess, the best way forward for them in waste heat and cooling recovery. This is not supposed to be the final, sort of piece of work that you would do on it. It's just to allow you to do a quick 30-minute sort of overview. Is there something here? Can I go further with this? Can I take this to my boss and say, give me some resource to now do a much more detailed assessment? That's what this is for. So once the user's actually gone through that and they've done that quick assessment for free at the soWhat project website that you can see on there, the user ideally would then come to the soWhat people, consultants, and say, okay, I think there's something to go at here, and I would like to look at this further. And that's where you would now start using the more advanced tool. Now, what you can see here is on a map all of the project demo sites that I think we saw earlier in different presentations, and as I mentioned, the one that I'm just going to concentrate on just to show an example of what we've done is the Italian demo site, but we can look at any of these in the actual tool that's been set up. The first thing that the user would need to look at and understand is what data they actually have at their facility, and what's available and how they can collect it. I think it's been identified by pretty much all pilot sites that data collection is actually a key issue and a key barrier to enabling you to understand what you can do with waste heat and what waste heat you have. So one of the first things that we've tried to do in the software is enable I guess a number of different routes through the software to give you easy data collection and data import. So you can, starting at a very detailed level, if you've got sub-meters and sensors on different processes, you can get that data and import that into the software. But if you don't have that, might have partial submetering, or even just utility bills. If you can just upload that overall utility bill, we can then actually start doing things with that, and I'll just show you in a second. So here, this is just an example of in the software. If you've uploaded some information, let's say here from a utility bill, that would information is interpreted in the software, and we can then actually map, because we would also ask you for all of your different processes and systems and all of their different parameters as well. We would then use that billing information to start mapping sort of these different power consumptions to those different processes. We would also ask for the hourly schedules of different processes and how the facility actually works. That enables us then to take different processes, different meters, different billing information, and associate it with the different components in a facility. And we can then build a profile of a particular process in terms of how much energy it's actually using, and also how much waste heat it might give off. We can then model this in here you just see a simple factory model, and those processes and components can be joined together. And we can actually also, in the software, look at different elements of HVAC controlling, and we can also look at different weather conditions that might be important for the future too, and we can simulate those. At the end of this data collection exercise, in the software, you actually come up on the top right there. I guess the graph on the top right actually shows not only your waste heat resource, but it actually shows that at a time series level, at an hourly level. I think that's quite key. You don't often see that. We're used to seeing maybe waste heat at a monthly or annual kind of figure, but actually being able to see it at a time step down to an hour is quite important if you're wanting to recover it and understand what you can do in your facility. So then we would move on just to try and understand this further. We can produce in the software lovely energy flows in these energy Sankey diagrams that really show you all of the energy inputs. And because we've got all the different processes mapped out in the software, you can see where all that energy is going to, where it's being used. I guess we would call it the sources and the sinks. And the top right-hand little red box at the top right-hand side of that energy Sankey diagram, that's the waste heat as a sink at the end of this flow. And that's where you would then look at to focus to recover your heat from. And obviously this also gives you some temperature ranges and outputs in terms of how much heat there is. In the software, the advanced tool gives you the ability to model things in a sort of a 3D, give you a 3D view. And we can also bring in anything to do with energy heat demand at this stage as well. So we're not only just showing potential sort of supply aspects in terms of waste heat, but we also import in heat demand from different buildings at this stage too. We also then start to set up a supply network. So here on the left-hand side, you see the supply for a particular facility in terms of its electricity and also its heat set up and how it's actually distributed to different buildings in this facility. And then as you go through this slide in the middle, we decided to try and add in a potential heat exchanger to recover waste heat and distribute it to the rest of the facility. And we also included more PV at the facility as well, just as an example to show what we can do. What's not on this slide is actually also the ability to draw in district heating networks. And it's something that we've implemented later on in this project in the software. So on here, if there was a district heating network, you could actually draw that network onto here, and you can actually show what types of pipes there are and all the different types of parameters that you would like to show as part of a district heating network. And you could then actually show where you could send that heat, not just in the facility but in the surrounding area. Once you've done that, that's your you would simulate all of that. But what we don't want to do is just leave that in the hands of very, all this work was done on a desktop. So you don't just want to have that on one person's computer, that they then have to sort of print off results and or download things and go and show people. So what we've actually done is take all of the results from this quite detailed analysis and brought it into online dashboards. So in a company or in an ESCO or district heating company, you can give access to all the results to as many people as you would like, and they can see that quite easily. So here you can see, I'm just showing online, you can see the 3D model view online that we set up. You see in terms of just the initial baseline, you can see the energy Sankey diagram that's available for people to look at, and you have all of the key indicators for what's actually currently happening with energy and heat and potential waste heat in your facility. From there, I know these graphs are quite difficult to see, but because there's quite a lot of detail in it. But here, this is actually showing final energy consumption through the facility, and on the left-hand side, I think it's showing the baseline scenario, and the sort of graphs on the right-hand side are showing different aspects of the simulations that we did around the heat exchanger and the PV as well. And so you can actually then quantify, in terms of final energy consumption, the differences in what you're looking at. You can also do the same in terms of the heat and electricity consumption. So here you will be able to see how much heat the facility was requiring, let's say in terms of the natural gas grid, how much it was using, and then also after you've done some waste heat recovery, you can then see actually how much you're using from the grid and how much are you now using in terms of waste heat, how much you're saving therefore. And the same with electricity, you can do that baseline against different scenarios. There's also the ability to see that in terms of CO2 consumption as well, or CO2 emissions. And then again, you saw in the free tool, we'd implemented quite a simple financial analysis. This more advanced tool now brings in a lot more elements that you can layer up in terms of your analysis. So this would be something that would be, you consider now pretty robust. You've gone through a very detailed sort of simulation of different technologies that is pretty robust, and you can now add your financial analysis onto that. And this would be something that if it was like a financial director, they would be very interested in. I think from different people I've spoken to in the financial community, they tend to look at a payback period of about 5 years to be something that they would really consider investing in a lot of companies. And so here, through the analysis that we did, you can see that the payback period is 4.5 years. So it's definitely worth looking at this example in this company a lot more. The other aspect that was also in the free tool, but it's also in this tool as well, is the business model part of things. So I think here, you're kind of looking at, the risk as well. You answer some questions on different aspects of risk, and similar to the free tool, you can really understand what that means for your company. And then here is the business model aspects of things, where the user just goes through a set of simple questions about the ownership, whether it's public or private, and who's actually running different aspects of, say, a district heating system, and who's doing the investment. And therefore you can come out at the end and try and understand what the best and most appropriate business model is for you. I should say on here as well, on anything to do with the online aspect in both the free and advanced tools, there's lots of eye icons on the page, and that either links you to on the page a pop-up that tells you exactly how things are calculated and where all the sources are and all the references are, or it takes you to the actual really detailed deliverables and research that has been done by this project that you heard about in the last few presentations, and that you can find a lot more about there as well. So thank you very much. That concludes my presentation about the soWhat tool. I think it's a fantastic piece of technology, and we've seen as a project group the work that's been done to show that actually there's nothing currently in the market that can do all of the aspects of what this software can do. And I would also add that the company that I work for, IES, in terms of the simulation abilities that we've been and the technologies that we've been able to develop from this project, this has now been released. This sort of piece of software has now been released as a final commercial piece of software in IES's actual business. So this is really taking research out into the market, which is, I think, what a lot of people would like to see. So thank you very much, and I'll take any questions.
Any questions so far? I guess not.
Thank you very much.
Sure. Thank you. So up next, we have the Alliance for Energy Cooperation in European Industries, addressing waste heat recovery from different perspectives. We should have the connection with Marcelino Gallego, the project manager at Circe and Coralis project coordinator. Do you hear me, Marcelino?
Yes, I can hear you.
Very good. You can...
Good morning.
Good. You have the floor.
Thank you. Do I share my presentation or?
Share screen.
Sorry, I cannot find the. Yeah. Can you see my screen?
Not yet.
No, can you see my screen now?
Yes, now we see it.
Okay.
Perfect.
Thank you very much. Okay. I will introduce Coralis, the Coralis project. Coralis project is a 4-year project with 29 partners, and we are in the second year of the project. This project includes 3 lighthouses where we will apply some industrial solutions, and also 3 followers which will learn how to apply industrial solutions. There are small projects where some industrial symbiosis solutions are applied. However, there are not too many big projects where industrial symbiosis solutions are applied. And there is a theory about industrial symbiosis, but not really applied on field, okay? And once the industrial symbiosis solutions are implemented in a real scale, there is a necessity to identify the factors which has influence in this industrial symbiosis solution. In this slide, we can see how is configured something what is Coralis. The project has been designed as a demonstrator project for a generation of a real experience on the development of industrial symbiosis. Coralis will develop a new technology based on the concept of a technology readiness level, and this new technology is called industrial symbiosis readiness level. The industrial symbiosis readiness level consists on 3 pillars: technological readiness level, economical readiness level, and managerial readiness level. These 3 elements are interlinked in an holistic way. I mean, the 3 of them has the same importance, and the industrial symbiosis readiness level also goes from 0 till 9. Before Coralis, there were some low industrial symbiosis readiness level in the lighthouses, and after the Coralis project, we will see how this industrial symbiosis readiness level will increase. These are the objective of the Coralis project. Coralis project is under the Aspire project. So this means that this is a project with high and intensive use of energy. And this, you can see the objective of the Coralis project. And we have the deeper understanding on the industrial performance based on some key performance indicator. Also, we introduce industrial symbiosis facilitator. I would like to mention that this industrial symbiosis facilitator were implemented as a neutral agent in order to support the project implementation and to help when we have some issues. Also, another objective is the profitability and sustainability of the industrial symbiosis opportunities, contribute to the decarbonization of the value chains and exploitation of the industrial symbiosis industrial area. And the last, but not the less important, because we realize that we are increasing the awareness of the industrial symbiosis solutions, because nowadays there are a lot of projects getting this implementation in the implementation of these industrial symbiosis solutions. In the impact of these are the impact of the project. And this impact or this specific objective will be measured in each lighthouses through individual KPIs. And each lighthouse will be focused more in the different impact, but all in all, these are the main impact of the project. We change toward a circular economy. We are improving we hope to improve at least in a 15%, the energy efficiency, to have a reduction of at least 30% in the energy intensive, also to have a reduction of 40% in CO2 emissions, and a reduction in primary raw material intensity up to 20%. Reduction of waste energy by at least 25%, and better understanding of relevant barriers. These barriers, we realize that mainly we have more problem in the regulatory barriers, at least. Also technical, but with the regulatory barriers, we have quite a lot of problems. Also, the dissemination of the major innovation outcomes and environmental gains. And the last and really important, the replication of the result of the industrial symbiosis applying the lighthouses and what we are studying in the followers in other scenarios. In this slide, you can see how the Coralis have been structured. There are 2 transversal activities, one for the management and another for the communication and dissemination. Then there is a baseline defined, In the demonstration activity, all changes to be implemented are evaluated using some tools and business models. Then the impact assessment and lesson learned are evaluating the situation. So we see how it was before to do the changes and how it will be after the changes will have been implemented. And finally, we have the exploitation and replication result of this project in another scenarios. Here we can see the first lighthouse, which is Escombreras. The facilitator of this project is Fertiberia, which is a large fertilizer company in the Mediterranean area. This lighthouse is focused in chemical, minerals, and water. Here you can see in a study which we are doing for a CSP plant to get energy for the desalination plant and also to get energy for a Fertiberia factory. Fertiberia is developing a model method to produce the fertilizer based on potassium nitrate using less energy. Then the waste of this process contains chlorhydric acid, and we will combine this chlorhydric acid, this substance, with some resins and also with CO2 or with sulfuric acid coming from a neighbor factory in order to remove the chlorhydric acid from the waste and use as byproduct or pure chlorhydric acid for the process. Below you can see the impact in which we can, which we are waiting, which we hope to get at the end of the project. The next lighthouse is based in Sweden. It's a pulp and paper factory. The location is in Provi, sorry. A tomato greenhouse and a fish farm we are building this greenhouse and the fish farm in order to use the CO2 from the pulp and paper company and also waste of the heat coming from the pulp and paper factory. Also, you can you can find the objective of this lighthouse or demo site just below of this of the slides. In this demo site, we focus mainly in the CO2 and in the wastewater. Okay, the fish farm is out of the scope of the project, even though it's going to be built in the same time. And the last one, we focus in Brescia, in Italy. Here, the use of materials such as steel, cast iron, and aluminum are the main product. Also, we will introduce a biochar coming from a local supplier. This project is enabling the recovery of industrial material to be used as alternative feedstock and therefore reducing the current landfill ratio in Brescia. And the biochar is going to be used instead of coal. Here there are the link. There are more links between different factories because some of them are moving material, waste material directly to the next factory to be used at the byproduct. And this slide, you can see the 3 followers we have in the project. In this follower, we are evaluating and learning how to use industrial symbiosis solutions. For instance, in the first one in Linz, in Austria, we are evaluating how to use green hydrogen coming from one factory or from one place to another factory. And the second demo case, forward is in Basauri, in Spain. This is a steel company where they want to use the waste heat to be stored in a thermal battery unit, and this energy will be used in the same factory, in Siderar factory, and also the possibility to be used as steam for another users. And the last one is in Izmit in Turkey, and we are studying the business case for definition how to use spent caustic in a potential users. And the Corallis status today, as I mentioned, we are in the second year of the project. We are just in the middle of the project. We have been dealing with many issues or different issues as the pandemic. We start with in the pandemic in January 2021. Then we got the energy crisis and this war situation having an impact in some of the partners, because some of the solutions we would like to implement in Escombreras, the supplier was in Ukraine, and they need to move all the factory to Poland, for instance. Also, there are some delays in the deployment in the lighthouses as a result of the increase of the project. Then also the baseline of the evolution, as I mentioned, the industrial symbiosis readiness level, we are evaluating continuously. We found some technical challenges, mainly in the CO2 capture from Froby from Sweden, and also some technical challenges with the biochart. And in legal challenges, as I mentioned before, mainly we found problems with the regulatory legislation, because, for instance, when you try to move some material which is cataloged as a waste in one company, this waste, when you try to transport, is under different regulation, if it's waste or if it's byproduct. And we found problems on how to get in the second factory or in the factory where this waste is going to be used, because there is a gap in the law about how to treat physically and with the regulatory condition for this kind of material. And also we are improving a lot of the awareness of this industrial symbiosis solutions we are implementing and founding. And we are also collaborating with some hubs for circular economy. These are the 29 partners we are in the Corallis project. And that's all for my presentation. Thank you very much for attending. And if there is any question, I'm really glad to answer. Thank you.
Thank you very much, Marcelinho. Up next, we have from We District, John Martinez, Project Manager at Acciona and We District Project Coordinator. Do you hear us?
Yeah.
Very good.
Hello. Do you see my screen?
Yes, we see it.
Okay, perfect. Thank you. Okay, hello. I'm John Martinez from Acciona. coordinator of We District project, which aims to demonstrate the combination of different different innovative renewable energy sources, thermal storage, and waste heat recovery into new and existing district heating and cooling systems. As you know, these district heating and cooling systems are a proven solution to provide thermal energy from a power plant, where the energy production is centralized to the end users through a network composed by insulated pipes. One of the advantages is that these networks have better energy performance values than the individual heating and cooling system, and this affects directly to the end user's energy cost. Also, another advantage, and it is very focused in this project, is that although there is a high amount of district heating based on fossil fuels, in this system it can be easily replaced or minimize the fossil fuel contribution by integrating renewable energies or taking advantage of other sources. The upgrade of this system is remarkable in comparison with other energy production and distribution systems. We District project started in October 2019 and ends in March 2023, though we are currently in an amendment process to extend the project to have enough time to construct and operate the 3 demo pilots we have. Also, we are 21 partners among 9 countries and a funding to complete the whole project of almost 15 million euros. In the consortium, there are large companies, SMEs, universities, and technology centers, which compose a well-balanced distribution between industry and research organizations. This is a photo that was taken in the General Assembly that we had last month in Bucharest. The project goal, as explained, is to demonstrate the innovative 100% renewable energy-based district heating and cooling solution, not only for the new system, but also to retrofit the existing ones. Among the technologies within the We District, there are 3 different solar technologies: a high efficient and low emissive biomass boiler, hybridization of geothermal and solar energy, an innovative absorption chiller, and also an advanced thermal storage. Besides these technologies, another objective of the project is the integration of a smart ICT to manage the production, storage, and consumption of DHC networks. The inclusion of accurate weather forecast and demand prediction helps to manage through smart control strategies the production and demand variables. In We District project, we will validate the combination of different renewable solutions in 3 pilots located in Bucharest, Luleå city in Sweden, and Cordoba in Spain. These projects engage all the stakeholders through the 4 phases within the whole process: the requirement analysis, the design and development, demonstration stage, and the final one, the analysis of the results and exploitation phase from technical, economic, and environmental point of view. In Cordoba, a new district heating and cooling will be constructed in the campus of the University of Cordoba. That is a partner of the consortium, integrating solar thermal technologies, low emissive biomass boiler, absorption chillers, and thermal storage. Yeah. In Bucharest, we are retrofitting the existing gas cogeneration district heating in the campus of University of Cordoba. This retrofitting is being done by integrating geothermal and solar hybridization to enlarge its heating and cooling capacity. There were some buildings that were wanted to be connected, but there wasn't enough power. In Luleå, we will integrate the data center waste heat into existing district heating network using a pioneering technology based on biogas fuel cells. Besides these three real demo sites, WeDistrict project wants to demonstrate the replicability of the project in different business scenarios through virtual demo studies. And for this purpose, 11 virtual demo sites will be simulated to evaluate the impact of renewable energies into new or existing district heating networks distributed across Europe. This activity links with the development of sustainable business model, which aims to demonstrate to investors the profitability of integrating different renewable energies combination. In general, indeed, economically, these projects are profitable since the OPEX are sharply reduced when compared with conventional fossil fuel-based installations, since we are using free renewable energy in the generation process. We will also develop an open source calculation modeling tool. This result will be a user-friendly program, especially able to serve promoters to get a first idea of the feasibility of a particular new or retrofitting project, where they would be able to compare different renewable energies combination, taking the outputs as key information to take this decision. In conclusion, the WeDistrict project demonstrates the advantages of integrating different renewable energies and waste heat sources into district heating and cooling networks through a better valorization of local resources. This is a key point, involvement of end users, and also the smart ICT to manage the whole process. Thank you for your attention.
Thank you also for your time, John. Up next, we have Emil Lezak from Incubis. He's an R&D project manager at ISNAB and Incubis project coordinator. You have the floor, Emil. Do you hear us?
Thank you. Thank you. Good morning, everybody. I'm going to share my presentation from my device. Wait a moment. I think. Please let me know if you could see the presentation in the presentation mode. Okay. Thank you once again. Pleasure to be here. My name is Emil Lezak from ISNAB, SME from Warsaw, Poland. ISNAB is the dissemination communication leader of the Incubis, which is the coordination support action under SPIRE initiative, almost on the last straight of the implementation. The high level objective is the decarbonization of the energy intensive industry in the Europe through unlocking market potential of energy symbiosis. This we deliver through creation of the virtual cloud incubators located in the 5 real location in the Europe, which I'm going to show in the next slide. The consortium is formed by eight partners. The project has been divided on the 3 phases, and now, as I said, we are on the last straight to deliver the virtual platform for incubators. However, we start this through identification and the mapping of the energy intensive industry, then characterization and of the needs and the gaps through analysis and optimization, all the aspects related with the synergy opportunities. And we also determine the economic feasibility for matching the stakeholders. Now we are in the implementation of the virtual incubators in different locations. Motivation as well as objectives was also a high level established for different kind of the stakeholders, which you could see on the on this graphic, and read what was exactly the motivation. In brief, was for economic and environmental purpose, means that to reduce the cost of the energy use and use of the relevant materials, as well as reduce of the taxes related with the waste landfilling. And from environmental point of view, reduction of the CO2, as I have been mentioned, and reduce of the waste for the landfilling direction. This, of course, related with the social benefit related with the municipalities which are connected to each of the incubator in our project. Here you could see the structure of the consortium and the main roles which has been performed by each of the partners, and location of the incubators, real industrial sites in the Europe. There are in the Spain, Germany, France, UK, and Norway. And on the following slides, I'm showing you just the picture of all the industrial location, which are cross-sectoral mix of the industry, non-ferrous, and cross-sectoral addend, respectively, to Barcelona, South Norway, and Hamburg region. Also in Dunking and Brunsbüttel, we have the industry sites characterized by chemical industry and iron and metallurgy. Then, as we are on the last step of the last phase of the project, I'm showing you the virtual platform models, which are different kind of the models for the different purpose, which you could see. Sorry, just wanted to move it, with the different functionalities, such as industrial symbiosis project management, opportunities screening, assessment, training and mentoring, as well as tendering, which you could find the description here. Sorry, I cannot move the slides. Well, the virtual platform, the incubator is already launched. You could go to this website, find it this interface, and log in, which login is free of cost, easy to perform, free steps, which takes a few minutes, giving just basic contact details, affiliation, and location. It is for any kind of the stakeholders which somehow is related with the energy symbiosis activities for the clients as a buyers of the energy located in different location of the Europe. Then showing you the first step, and you could at the end of the registration, as I said, which is quite easy to do it. You could find the main dashboard when all the components are already embedded and full functionality as this stage, and through simply searching. This is just example for the Barcelona region. You could find different companies related with the energy intensive industry, with the main characteristics, main needs related with the energy and energy waste. We have already delivered some showcases. Here are those showcases related with the previously presented Barcelona incubator. If you go deeper for each of these showcase, you could find the more detailed description related with the use of the energy and other kind of the characteristics needed to start creating the matchmaking between each of this company and possibly buyers of the energy. We have also included here some of the webinars which has been organized and delivered by the Incubis partners, and you could find it there in the PDF files and be more engaged in our project, Incubis project. At this moment, we have launched this. We want to officially perform the communication campaign at the end of this year, which is already now. And since January up to April next year, which is the end of the project, we want to perform the replication study as well as training events for each of the regions which I present on the previous slides. Then thank you for your attention. I'm open for the discussion. Here you could find my contact dates or just scan the QR code. Thank you very much.
Thank you very much, Emil. Our next speaker, he's a project manager at LE2C and ACES project coordinator. Unfortunately, he could not be live with us, but we do have a pre-recorded message from him, Fabrizio Guarassi.
Hi all, nice to be here. So sorry, in fact, if I cannot be live here, but I had an inconvenience, so I will record my speech today. I am Fabrizio Guarassi. I work for the Lombardy Energy Cleantech Cluster as project manager, and today I'm going to present our project, ACES. RACES, in which the acronym is Framework for Actual Cooperation on Energy in Sites and Park, is an European project founded by Horizon 2020 program, and is composed by 8 partners from 5 different European countries. And our consortium represents the entire value chain necessary to foster the energy cooperation project, so such as suppliers, ESCOs, clusters, and so on. So why our project is focusing on industrial sites and park? Well, you have to imagine that from the total demand of energy in Europe, the 25% came from the industrial sector. From this 25%, only the 16 came from renewable. So we really believe that in this time of energy crisis, industries need to know how to save their energy. Well, how can they do that? The answer is short and clear for us, and is energy cooperation. By exchanging surplus of energy and tying everything together with smart energy management system. So the focus of our project is to turn high potential and high impact industrial cluster into ecoregion. What are ecoregion? Within Oasis, ecoregion is a geographic area in which there are energy and information exchange between stakeholders of different typology. The general aim, the general aim is to reduce the energy consumption through the utilization of surplus energy, and the target is that in that specific area, we will reduce the CO2 emission by at least 10%. How we do that and how we build ecoregion? We developed 3 practical tools that allow stakeholders to foster and to start the energy cooperation project. The first one is the self-assessment tool that facilitate the process of collecting the necessary information, energy information between your industrial neighbor, and basically allow you to get a picture on a specific area on the energy potential of your industries close to you. The second one is the legal decision support tool, and say, okay, well, after the first tool, I know the energy potential of this specific area, and I can know if I can build an energy cooperation project. How we build concretely the energy cooperation project? Through our second tool. This is the legal decision support tool that help you to drawing up a contract in easy way, thanks to our format, and between 2 or different entities. Third one is, okay, first one, I know your energy potential. Then we built our legal contract. Okay, let's manage our energy stream that we are exchanging. How we do that? Thanks to the third tool, that is the energy management platform. Basically, it's a software that allow you to manage and have a better control of your energy exchanges. Sorry. Here I also included a QR code that allow you to directly link to our webpage, in which you can find the 3 tools in more detailed way, and then you can use it because they're totally available and free to charge online. Within Races, we have 3 pilot ecoregion that allow us to test in a realistic environment the tools and the target that I briefly explained it. The 3 target ecoregion are Antwerp in Belgium, Nyborg in Denmark, and in Lombardy, sorry, Bergamo in Italy. Within Bergamo, we started our work by focusing on existing project that is called Bergamo Plus Green, Bergamo Più Green in Italy, which will forecast to construct the construction of a new DHI pipeline in the early of 2023. This new pipeline will connect waste to energy plant to an existing district heating system in the city of Bergamo. As you can see in the slide, the new project is represented. We'll collect the dot 1 to the dot 2, and basically is the new green line. Okay, you can see here, this is the new pipeline, and then the green, the red line that you see here is the existing district heating network. So what we did is to starting from existing district heating network, the project, so the green line. We mapped the old industrial area along the new pipeline, and yes, is the areas that you can see here in red. So we mapped all these area. Thanks to the self-assessment tool, we analyzed around 15 industries, and what we did is also we discovered, you know, the profile of each industry and the energy potential. Among all, sorry, among all these 15 industries, we found a paper mill factory that was particularly interested, and here is shown in the dot blue, number 3. So the paper mill was chosen for the amount of excess heat that the paper mill could potentially supply to the district heating. So thanks to the self-assessment tool, we discovered that this paper mill had a cogeneration plant that produced around 700 kilowatt hour of hot water during the paper production, but just a small part of this was used inside the production. The rest was totally wasted. So we presented this potential use case to the district heating owner, that after several meetings and discussion, they took the opportunity to link the paper mill to the new district heating network here. So just here I summarized the process. As you can see, basically the paper mill will sell all the hot water to the district heating and will buy just the right amount of hot water that needs for the paper production. This process, as you can see here in green, in this scenario, brings positive impact in terms of cost reduction, that is around 62K per year, and also that area. In that area, after this project, will save around 4.2 tons per year of CO2 emission. So this brings benefit to paper mill, to the district heating, and for the entire city of Bergamo. Currently, the paper mill and the multi-utility are defining the operational part, let's say, and they are working in the legal aspect by using our legal tool. So our tool now is helping them in totally easy way to found the legal part and to agree on a specific aspect on energy cooperation. Well, the vision of our project. Our project is not limited to just the 3 pilot ecoregion, but we want to open the door to other industrial parks. We want to, let's say, replicate the success that I showed in the Bergamo region, and let's say we believe that, and what we want to do is that industrial sites and business park can turn their energy potential into energy hub. For us, the energy cooperation is the solution, and the vision of our project is to keep promoting the transition to a circular economy model based on heat exchanges and, of course, industrial symbiosis. So if you are interested in exploring your energy potential, if you are interested in getting to know our project, or if you want to just to get in touch with our consortium, please scan this QR code and let us know how we can help you. Thank you.
Thank you very much, Fabrizio. Up next, we have Jose Maria Cunha, the project manager at INEGI and Ember's representative. Do you hear us, Jose?
Yes. Good afternoon, everyone.
Hi.
You can see my presentation?
Yes, we can. Yes, we can. You have the floor.
Oh, thank you. I'm going to present Embers, which project overview. So this is intended to be a heat and cold matching platform. The project itself is a Horizon 2020, similar to the other projects presented before. We have 16 project partners, 7 case studies, and it was intended to be completed in 3 years. And we just extended for 6 extra months to finish the case studies validation. You can follow us via Twitter, LinkedIn. Just follow the Embers project, and we have a platform which is embers.eu, and you can see all the information relevant to the platform. So the main objectives of this platform was to develop an open source energy modeling platform to identify feasible solutions for the recovery and use of excess heat, industrial excess heat mainly, but there are other options such as supermarkets, data centers, which we consider also as other industries. To simulate alternative technological or business scenarios, and to be independently used by a wide variety of industries and other stakeholders at various EU geographies. So, as been said, the main goal is to promote the integration of excess heat via either inter or intersectorial heat networks. So we can, and the main functionalities would be to map excess heat sources, sinks, and existing heating networks. To be run in a collaborative mode with several different users, and to perform different types of analysis whilst maximizing either environmental or social benefits, maximizing revenue, or maximizing energy into implementation, as to trying to promote the most excess heat to be integrated. It's intended to be a user-friendly interface to analyze multiple scenarios, as been said, and with different output formats or reports. So this is just a sneak peek of the platform. It is still in beta testing. So the user would enter, he would just see a map, and then he can upload objects, being them either sinks, sources, or links. Sinks are consumers, sources are producers, and links are existing networks. And you can input your details, and then you will have another part of the platform where you will test different scenarios, simulate different scenarios. And the platform itself is composed by 4 modules and a knowledge base. And just a brief description, the core functionalities, all of this is open source and you can find it on the internet, all the code. So the core functionalities, the idea is to determine the quantity and quality of excess heat. Then we have the GIS module, which is a mapping algorithm, trying to optimize the least cost pathway and linking demand and supply nodes. The techno-economic module will scope out different technical options of recovering, distributing, and reusing excess heat. The markets module to try to make a valorization of excess heat under different ownership scenarios and different market structures. And the knowledge base will be the database for all modules, compressing different technologies, simulation, default set, data sets, market regulations, and tariffs. And it's currently being tested and more users are welcome. Yes, once we finish the platform validation, I invite everyone to try and test the platform itself. So the case studies, we have some industry-focused case studies, such as cement plants, where they want to assess internal heat recovery options and also what to do with their excessive excess heat, so to provide to a heat network or to provide electricity. Some foundries in the UK, which they intend to perform a similar optimization. An industrial park in Greece, where we have multiple industrial sinks and sources, and we are assessing a heating network for the cluster itself. Then we have a district heating cooling network in Portugal, which intends to assess industrial excess heat to provide to the network. That it's already been built. It's already built. Then in Sweden, we have a similar scenario where we have an existing heating network, and they are going to extend to 4 new users, being 1 source and 3 sinks, and they want to assess what's the best connection possible. And then we have also super user, such as an example is ADEN, which is a Portuguese energy agency, and they want to assess multiple data sets for various regions, and they just want the Embers platform to give a quick assessment of what are the best or the most technically feasible synergies. And also, I just want to say that also we have for the market case, we have a peer-to-peer heat markets with the excess heat being tested in Denmark as well, where they are extending the capacity of the existing district heating network with local excess heat, and they are exploring different market configurations, such as supermarkets being used as a consumer and a producer, being which what we call a prosumer. So the platform, as I've said, it's available on the website, which is embers.eu. You can follow us on Twitter and LinkedIn and Embers Projects. And we hope to hear some feedback from you. Thank you very much.
Thank you. Thank you, Jose. And now we break for lunch. I would ask everybody to be back here at around 2:15 in an hour's time. Thank you all. 1, 2, 1, 2, 1, 2, 4, 4, 4, 4, 4, 4, 2, 2. Da, merge. Domnul Eden, pregătit? Dar ți-a venit să luați un microfon. Da. Hello everybody, welcome back. I hope you had a good lunch. For the first part, we will have a few words presented by Mr. Eden Mahmut on behalf of the mayor of the city of Constanța, Mr. Virgil Chițac. You have the floor, Mr. Mahmut.
Once again, hello everybody. So for us, it is a huge privilege as the Ovidius University of Constanța to have you all here and to celebrate a very important moment of presenting the tool, presenting the achievements, and to pack all of them and to put them in the service of all the other people that are interested on the outcomes. So in this context, it was also a very nice opportunity here in Constanța to visit our city and to meet also the mayor of Constanța. The meeting was day before yesterday, and on that occasion the mayor of Constanța, Rear Admiral Virgil Chițac, he presented his appreciation for what has been done by this consortium. It has been also mentioned why this project was so important also for the city of Constanța, because here, as you can notice all around, there are so many works that are taking place at present. It was a huge program that was launched for upgrading the infrastructure. Among the infrastructures that are in the refurbishment process now, let's say, district heating infrastructure has a priority. And as you remember, the mayor pointed out that for that reason, it has been so important that a team from the Termoficare company, which is the company of the municipality, was involved in this project. It has been the possibility to contact the very important experts and companies, universities and other experts, and to take the advantage of this knowledge, to share this information, to learn from this experience, but also to develop the ties and different other opportunities for collaboration. So from that perspective, this was a very important aspect. The second aspect that was also mentioned by our mayor, it was the fact that the municipality of Constanța, of course, is facing a very difficult period. Here in Constanța, we are very close to an area of conflict with many consequences, with many refugees that have been located here. And in this very complicated context, we appreciated more what is the real reason of the European Commission to push forward on the decarbonization, to push forward on the increase of the share of renewable energy, and in this way to assure the energy security of this area, but not only of this area, but of the entire Europe, and in this way, of course, to assure a better future for Europe. So from that perspective, the mayor of Constanța, if you remember, underlined the commitment of this municipality for promoting renewable energy, for promoting, let's say, the possibilities to use the waste heat, and at the same time to put a strong emphasis on the sort of holistic type of approach. So once again, the mayor excused himself that he could not join also this meeting, but his message is extremely important. You remember that he appreciated the fact that this consortium succeeded to develop this tool, which is a very important achievement. And now with this tool, we are in the position to start building different application cases. And of course, finally, the mayor invited to not stop here, but to go further with other project proposals. And in that context, he assured all of us of all support of the Constanța municipality for future projects, and particularly his interest to transform Constanța as a pilot, as a success story, not only in Romania, but in whole Europe. So with such a commitment at that high level, I think we can do many, many things. Thank you.
Thank you also. And we are about to start our second session, and I believe Eden Mahmut is actually the member of the Consultative Council for Sustainable Development for the Romanian government, but also soWhat's responsible for the Romanian demo sites. And I presume you have the floor now to present the results.
Well, I put the new hat, and now I shall try to summarize the, let's say, activities that we have developed under the soWhat project. Once again, it was a very special project for us. We could say also a project that changed a little bit the game here in the city of Constanța. So, cum facem să facem? Yeah, now once again you can see the whole story up to now, which was quite nice, very interesting presentations. And we would like to continue this with the current and specific situation here in Constanța, where, as you know, we have inherited a very important infrastructure for district heating, which has been developed in the 70s, and at the same time, this strength has also many weaknesses. So from that perspective, for us, it is extremely important to move beyond this. And is coming. So, you have seen that the city of Constanța, one of the very important urban agglomerations here in Romania, is hosting the largest port of the Black Sea, and at the same time has the characteristic of such a port city, because as you can see here, the source of thermal energy was developed in the 70s as a cogeneration plant located in the industrial area of the city, in the south part of the city. The city, over the years, has been expanding towards the north. So in this way, it was an asymmetry of the piping system, of the district heating system, with an extending, let's say, distance from the heat source. And this was a major problem for the future developments. You can see here some of the details of the areas of the north where there were some problems in assuring the quality of heat due to the distance that was from the source. So what is the challenge? You have seen that at present the district heating company here in Constanța is operating more than 50 reheating units. And in these reheating units, in each of them, there are different type of allocations of blocks of dwellings connected to such reheating systems. As you can see here in red is a reheating system assuring the thermal energy for the blocks that are around. So in that context, I don't know what's going on with this. So, the major challenge is to find out a possibility how to reduce the environmental impact of these heating systems and processes within the city. You can see the balance and the consumptions of energy, thermal energy, in one of these, let's say, heating units, the heating stations in the city. You can see over the year, the consumption is covering some important quantities in megawatts. Then you can see the equivalent natural gas consumption, the equivalent CO2, let's say, of the emissions related to the production of the thermal energy based on fossil fuel. So the idea was to develop an approach to, let's say, reach the current level of development of the district heating systems, where you know that we can integrate all types of renewable sources in order to assure a sustainable operation of such a system. So for that reason, as I said, we took as a pilot such a unit here in Constanta. We have studied the resources of solar energy that are available on that location. We have analyzed the matching of the solar energy with the consumption. And based on that, it was developed this concept, having, as you can see here, on the top roof, 120 solar thermal panels. And inside the station, there are these two boilers, pellet boilers, for covering the peaks and the required additional energy when is needed. So we developed different type of analysis. This is a model of that. And then we had this chance to work with the soWhat tool. So succeeding in this way to develop the model of this plant in the tool. And then, of course, we developed the aerial model of the location. And you can see here that it was imported also the buildings and particularly the secondary reheating station. And now there are different activities that we are carrying on. Our colleagues from the company Termoficare, they already procured an equipment for thermography and to identify the losses over the entire value chain from the power plant to the final use. And then we started also to identify additional problems. The city is a city located near the sea, is very windy, and also in the atmosphere there is a lot of dust. So the dust usually is depositing as dust and dirt on the surface of the solar thermal panels, and there are problems related to the decrease of the performance of these solar thermal panels due to the dirt. For that reason, in this institute, some of them you have seen that just next to this building, we have our Institute for Nanotechnologies. We developed some anti-static solutions in order to protect the active surfaces of the solar thermal panels in order to reduce the deposition. And in this way, to go further and to have these solar thermal panels with high importance. Then, of course, we analyzed also different other possible risks that could occur in the operation of the system and to identify all these risks. And finally, we presented to our mayor the concept of an island, an insularized area of Constanta where 6 these kind of stations can work together and help each other transferring from one to the other. So besides of that, of course, we are planning in the future to look to other cities here in Romania. For instance, in Galați, there is a city where there were experiences in using the waste heat from the steel industry for the district heating system. In Brăila also, it was a large chemical plant that was also operating together with the district heating of the system, and we would like also to evaluate this. In Brașov, located in the center of the country, there were many collaborations with the local industries in order to bring in different waste heat from the industry, and in this way, we think that it will be a very nice way of using the outcomes and the tools and all the experiences of this project. So thank you for your attention.
Thank you also. Thank you very much, Mr. Mahmoud. Now next we have Sofia Klugman, Research and Project Manager at IVL, explaining a little bit about the Swedish demo site experience.
Hello again. With me I have Anders Strand from Gothenburg Energy. At Gothenburg Energy they have had industrial waste heat collaboration since 1985. So that's why we're here to... yeah, I need this. So in this project we have used 2 sites in Gothenburg and in Varberg on the west coast of Sweden to verify the outcome of the tool. And also to see if there are further possibilities of using the waste heat in these cities. So in Gothenburg they have used the industrial waste heat since 1985, and in Varberg they didn't have a district heating network until year 2001, when they started directly to get about 90% of their heat from a pulp mill, which is rather close by. So, you want to say a few words?
Yeah, my name is Anders Strand. We'll talk about Gothenburg Energy. It's a company, we have several projects, district cooling, district heating, electricity, fiber and gas. In our district heating system we have roughly 17,000 substations and 3,400 customers, and the network is above 1,000 kilometers long. As you see on the graph there, in the bottom we have from waste incineration roughly 200 megawatts, and the 3 areas below, above there are refineries. So that is the waste heat that you collect in our system. No, back here. And also the color above are when in the winter, because we need more power than we also use wood chips for burning and heat pumps and etc. to manage the 1,400 megawatts that we need when it's cold in Gothenburg. We also have this district cooling system where we use the waste heat in the summer in absorption chillers. So roughly 50% of all the energy that we, cooling energy that we sell is coming from absorption chillers, and the rest is equally divided between compressor and free cooling from the river. So we use free cooling in the winter from the river, and in the summer we use absorption chillers, and when that is not enough, we have compressors to fill the peak load. During this project, we have installed a lot of sensors in our network and also in production to collect data for analyze.
Yes. And then a few words about Varberg Energy. It's also a municipal energy company, a smaller city than Gothenburg, but anyway. And as I said, no, it was 2001, I think. Yeah. And the distance the total length of the district heating network in Varberg is 140 kilometers. And as you see here, the yellow part is, or green or whatever, is heat coming from the pulp mill. But as you see here also, you can imagine that the pulp mill have a lot of extra heat in the summer. And Varberg Energy is therefore planning to build a district cooling network. And during this project, Varberg Energy have also enhanced the data monitoring. We have tested this district cooling scenario with the soWhat tool to verify the tool, to see that it gives the same outcome, you can say, as the feasibility study made by the Varberg Energy themselves. So, you know, Sweden is not a very hot country, but still district heating is cooling is an increasing demand, especially for offices, you can say. That is the big increase. They will use now coal produced from the industrial excess heat with absorption chillers, and this will be combined with free cooling from the sea. And by doing this, they can avoid to build more cooling towers at the pulp mill. So it's a win-win, as we talked a lot about. And here on the picture, you can see Varberg city, and in the horizon, you see the pulp mill. So it's quite a long distance. So in the economic feasibility, we can see that the payback period is about 22 years. It's the same result as from their own feasibility study. And when we look at the environmental impact, since the cooling today is made by electric chillers, and the electricity mix in Sweden is it's a very small CO2 emission from it. So we will not see a large reduction of CO2 emissions. But what the city still thinks is that this is worth to do because it will reduce noise in the city, and it will be a more environmental friendly system due to the reduced use of refrigerants. And it will also unload the electricity distribution network, which is a problem in many Swedish cities, that the capacity is full, so you cannot expand the city. And with the coming electrification of the transport sector, for example, we really have to think of reducing the electricity demand in different way. So there are several goals that will be fulfilled, even though we won't see a large CO2 reduction. Yes. So finally, this is what it looked like in the soWhat tool when we did the economic feasibility study, and you can see, well, it's the same result as in the facility's own feasibility study, that the payback period is 22 years. You can see. Yeah, that's what it is. Any questions? Yeah.
Thank you very much, Sofia. And now I would like to invite to tell us about the Italian demo site experience, Sabina Fiorò, project manager at NV Park, and soWhat's responsible for the Italian demo sites.
Okay. Hello, everybody. I'm Sabina Fiorot. I work in Environment Park. It's a technological park located in Turin, and we are mainly involved on environmental fields. Now I represent the Italian cluster that is made with the participation of Rina Consulting and the involvement, yes, of the demo site Martini and Rossi. Martine Rossi is located near Turin in Pessione. It's an industrial site and they produce mainly sparkling wine and liqueurs. And this demo site was identified as particularly very interesting to use the soWhat tool in order to identify economical, environmental benefits for the use of this tool. So just some indication, the overall cooling production is about 10 gigawatt hour per year. That is divided in different areas of the plant. So considering also the remarkable amount of low temperature fluids related to this production, Martine Rossi is very interested in analyzing the possibility and potential benefit of the tool. So linked to this, the plant produces a large amount of low temperature waste heat, which is cooled in evaporative condensers, and it accounts for about 15 gigawatt hour per year, and this is the potential that can be used and identified in soWhat tool. So linked to this, the main idea of Martine Rossi was not to sell or to use outside this recovering waste, but to find and to use internally in the plant. So they identified also other scenarios, so the sparkling wine process optimization. Also they have PV panels. They also thought about to use also this kind of scenario. But what we present now is the scenario that was used mainly for the soWhat tool, so the cooling tower, as a case study that was useful for the trial. So linked to this, the process consists of an heat recovery from rooftop condenser of cooling plants for process. Cooling plant use a refrigeration gas, typically Kelvin, based on Kelvin cycle process. The temperature of condensation is around 35 kilowatt degrees, and there are 10 condensers that are in the process. So what they also identified is that the main technologies that can be used to recover this waste is an heat exchanger for the sparkling wine process, and it can be used as water-cooled organic fluid condensers. The potentially recoverable heat is around 1,800 megawatt hour only for sparkling wine line. And the process will also produce hot water, reducing the natural gas that is mainly consumed in the boilers and CHP plant. So here are some details of the process and also temperature of the plant. So linked to this is just a very useful scheme that identify the use of this heat exchanger in order to recover the hot gas that come from the compressors. The heat is used mainly to warm up the environment and mainly only during the winter period. So you can check here the main circuit in which the heat exchanger, the idea is to install. So linked to this, what they have done is to include this calculation, this consideration under the soWhat tool. What is possible to recover is natural gas, and that is the energy vector, and it's possible to have 350 megawatt per hour per year as heat recovered that is an input in the soWhat tool. So in this table report the energy recovered to produce heat. These are the main numbers that are put as input in the soWhat tool. The initial investment is 180,000 euro. And linked to this, this is the main cash flow that is possible to have, and it's the result from the tool. So you can check internal rate of return, discounted payback, and also the net present value that come from the tool. Also here some risks that are a risk table, as also Nick presented this morning, so that is linked to the output of the tool. And then also here, as I said before, so it's possible to choose the technology that can be used for this recovery, so it needs a change. And also here we have some risks that are linked to this kind of technology. They are not so much high, this risk. The only is connection to lack of heat that come from the lack of the use or the functionality of the evaporation tower. So linked to this, these are the main results. The net present value we checked is around 300 kilo euro. The internal return of investment is 26%, and the payback time is 4.5 year. Linked to this, we have also a calculation of the avoided CO2 per year, and linked to the 20 years of the investment for our idea and our project. Just some lessons learned that come from this, the use of the tool. The main starting point are, as I said, to define the hot gas temperature and pressure, so some data that come from, that are the input for the soWhat tool, identification of annual compressor use rate and recoverable energy, and also definition of technology and scope. The main difficulties are mainly linked to the data collection. So because they are plants, they have yes, some measures that are along the plant, but this is the main difficulty. And also difficult to define data about the potential energy use, such as the department heat requirements. And the main results, as I presented before, obtained, linked to the scenario, the potential energy saving rate, and however, the low temperature involved make the application range limited to this use. But yes, the soWhat tool helped on this aspect, just to identify the main solution. So that's all. I thank also Martine Rossi also for this help and structure. Okay.
Sure, thank you very much. Next, we have Bob De Meyer, project manager at Kelvin Solutions, and soWhat's responsible for the Belgium demo sites.
I'm going to stand there and I can better look to the screen. Okay. Well, welcome to you all. I'm going to talk you through the Belgian cluster. We were our contribution to the soWhat project is mainly the development of feasibility studies and validation of the soWhat feasibility tool. So I'm going to talk you through our 2 demo sites we used to validate the feasibility tool, and give you a little context on the demo site. Our first demo site is Umicore Olen. It's a large large metallurgy company. What we analyzed there with the soWhat tool is that there was a lot of waste heat who could be recovered from the economizer of the combined heat and power plant. But the problem there was that the heat was derived through steam net, which has higher temperatures than economizers. So we looked to the processes, the industrial process they have, and the main processes are underneath 190 degrees. So we could reuse the temperatures from the flue gases from the CHP plant. And that's important. Of course, we have to build then an internal heat net, so the waste heat coming from the economizer is used internally within the Umicore site. Doing that, we can save a lot of gas consumption. Actually, there is at Umicore we detected with the soWhat tool. We can gain 38 gigawatt hours of waste heat using the economizer and transfer it into hot water. The net avoided CO2 emissions is about 3,000 tons CO2, so that's a large amount. Okay, knowing that, we put in a business case in our feasibility tool, and you already see on the first slide some difficulties we encountered, and the results also from the feasibility tool. We compared it with our validation tool, and we saw some small differences on the internal rate of return on economic side in Umicore. It's a it are small differences, mainly because the heat is internally used and prices are near to each other. The differences are derived to differences in the tools, where the validation tool has phasing in time of investment, phasing in time of avoided reduced gas consumption, and taking corporate tax in account. And there is also a separate indexation of the energy prices, which is not in the soWhat tool. So it's just another approach, but we have to compare it to see if we become, in the end, we become the same results. If we look at the differences on the Umicore side, we see on internal rate of return and payback period, but also on netto present value, small differences. Whereas in the soWhat tool, we become an internal rate of return of 19.83%. In the validation tool, it's about 19.03%. So that's very near to each other. And also on the netto present value, there is a slight difference. We looked up the differences, and we looked up the differentiating parameters, as I mentioned before. Of course, doing the project in practice on the Umicore side, we're not going to invest everything in the first year because you can't build it in 1 year. So there we put in a phasing in investment over 2 years, and also a phasing in time of avoided reduced gas consumption, because the users of heat, we cannot revamp them to hot water in 1 year. It goes in phases. Also divided over 3 years. We've taken corporate tax in account, and there was separate indexation. That's why that explains the difference that there are in results. If we put those differences to 0, you can see that it has the exact same result, the soWhat tool, as the validation tool. So that's quite good news for us to see that we've built a tool who can completely be validated. To have a larger stretch, we also validated the tool on a total different demo case. Next demo case is the waste incinerator. The difference is here that to reuse the waste heat, to valorize it, we have to sell it outside the borders of the company, outside the company borders of ISVAG, to a company, Atlas Copco, very nearby. We saw a potential of 38 gigawatt hours on a year base for waste heat. It's a very continuous source because it's waste incinerated. It incinerates all year long, mostly at the same level. And the demand we detected with the soWhat tool on the Atlas Copco site was about 10 gigawatt hours, mainly in the winter. So the match is absolutely perfect to do. Also, we've put in the results, the economic parameters to see what feasibility will give from results and how wide the spreads would be between the soWhat tool and the validation tool. You can see here that the spread between the results is much higher. On the validation tool, you see that it has a higher result, as in all other demo cases, we see that the soWhat tool has a higher internal rate of return. Here it's the opposite, and it's just because you're bringing the heat outside and you're selling it. And if you're selling it and you do a depreciation on the money you spent, but you do not take indexation in account of your income, you can have this spread. That's mainly the conclusion. Once again, you see here the differences, and you see also we've simulated the ISVAG case a little bit later with an indexation of 4% on fossil fuels. I think it's now much higher, but it's already higher than the Umicore case where we pointed out 2%. And it's mainly this factor who is responsible for the spread between the results. Once again, if we put the differentiating parameters to 0, you come totally the same result between the two tools. The overall conclusion is that certainly for internal reuse, soWhat tool is a very good tool and point out whether a project is on economic size is interesting or not. And I think for larger cases where you sell a lot of heat to the outside world, it's very interesting to in the commercial tool to include indexation of fossil fuels. So I don't know if there are any questions from the audience. If not, I would like to thank my soWhat partners and especially the industrial demo partners. Thank you.
Thank you. Thank you for that. Following now is Mr. Pedro Santos, founding and managing partner at To Go Out Consulting, and soWhat's responsible for the Portuguese demo sites.
Good afternoon to all of you.
I think he took it with him.
Yes. I will present the Portuguese Lipor demo site experience. Okay, I'm just waiting for the... here. Okay, sorry. I'm not seeing. Okay. So, this cluster has 3 partners, To Go Out Consulting as a leader of the cluster, the Lipor, the waste-to-energy company, that is an association of 8 municipalities of Porto greater region with more than 1 million inhabitants, and the Energy Agency of Porto as well is a metropolitan energy agency. We work together during this project Let me shortly present to you the reference scenario that we have been analyzing during this project. As it happens in Belgium, we have a waste-to-energy plant treating 380,000 tons of urban waste per year. We have considered a unique end user of the waste heat that could be recovered, which is the Porto Airport. They have natural gas boilers to provide the heating they need, and they have the electric chillers for the cooling function. So this is the reference scenario. In this, you need to be aware that in the waste-to-energy plant, they produce steam to produce electricity, and from all the electricity produced, they export to the grid something like 90% that they sell to the grid. The idea is to use the excess heat nowadays not used to. The idea is to recover this excess heat and to create a new district heating to connect Lipor waste-to-energy plant to the Porto Airport. We are talking about a 2 kilometers distance. We are for this, considering the thermal energy needs of the airport, they need 26.8 gigawatt hour per year, and for that, to provide that, we need to assure waste heat recovery of 40.8 gigawatt hour of waste heat at waste-to-energy plant. That's the big, those are the big numbers. Of course, Lipor has more waste heat recovery potential. That's why we have been considering, and we have already identified 2 new potential users. Emmanuel from the Adeporto already interviewed representatives of Superboc, which is a big brewer factory nearby Lipor. We are talking about less than 4 kilometers of distance. As well, the Leonesa Business Hub, which is another new potential users for this district heating. We are talking of considering the possibility of building a district heating to provide heat to the airport, and a complementary district heating to provide heat to waste heat to these new 2 new potential users. This is the complementary scenario that we are right now closing the modeling to try to figure out the big numbers about this potential. Considering the investment that it was analyzed for that, and talking about the main scenario to provide heat to the waste heat to the airport, Lipor needs to install an heat pump in their facility, plus investment on absorption chillers to provide the cooling, to assure the cooling needs of the airport, and pumps, heat exchangers, as well all the hydraulic district heating network. We are talking about not 2 kilometers, this is the distance, but 4 kilometers, because we need to consider the return. So this is the main investment. We are talking about something like 6.6 million euros of total investment, considering all this equipment. During the project, during this year, we performed several tasks to test all the functionalities of the soWhat tool. I would like to refer that during this process of installing and testing all the the modules of the soWhat advanced tool and to upload all the data, all the information that it were required during the process. Emmanuel, as I said, talked with Veolia, ourselves also with Veolia. We supported all this process of estimating the waste heat production and this investment, Superboc and Leonesa. So it was also a process that included some talks with the stakeholders. This is all the activities performed during the process. I would like to show you some of the outputs. This is some print screens of some of the results to use the different modules. This was one of the most challenging activity, which was to import and to format and to upload all the data required by the software. But we have been succeeded with this task. Another example of modeling the buildings, in this case of the airport. As I said before, 2 kilometers of distance from Lipari. It's not a big district heating network, so it won't be a so big investment. These are a picture about the building modeling of the two new potential users, 4 kilometers distance from Lipar. Another print screens of the software, and this is the network, the district heating network, considering not only the airport but also the two new potential users. We are closing, as I referred, we are closing all the estimation and all the calculations and I think that during next week we are going to conclude this work to consider this replication for these two new potential users. This is the feasibility study. I need to mention that in the beginning of the project we have a different technological solution for the waste heat recovery, and in the last months we concluded the update of the technological solution. That's why we are closing this analysis. This is the big numbers. You can see the total investment considered, almost 7 million of investment. You can see in up left the total capacity of waste heat production for the airport of 40.8 gigawatt-hour, and the energy that will be provided to the airport needs the 26.8 gigawatt-hour. Considering this, we have achieved these results. As Bob referred in the previous presentation, the use of this module doesn't consider the phasing of the investment. It considers that in the first year we have all the capacity of getting the profits from selling the waste heat, but but to build this, to put in the field all these equipments, we will need, and the network, it's the main work in this investment, we will need for sure at least 2 years. So we have 2 years of delay to achieve this, but we can consider that this is the economic science, the third year after all the investment, all the equipment being installed, all the network being in the field, and the full sales system 100% of capacity for operation. So the results, it were very interesting. We are talking about a payback of less than 6 years, and we are not considering the possibility of getting some kind of funding, because LIPOR is an association of 8 municipalities. To implement this investment, for sure they will need, because we are talking about 7 million of euros of investment, they will try to get some kind of funding to this to support this initial investment. So the economics are interesting, but now we are finalizing the sensitive analysis, because we need to consider if the electricity prices rise, if the prices to sell the waste heat is not, it couldn't be so big as we have considered. We need to try to understand which impact from the economic point of view these deviations could have on the business model that we have studied. Using the advanced tool, we also analyze the risks and the likelihood of the occurrence of each risk. This is what you are seeing here. And we already have chosen several options about the business model. This is some functionalities that were available in the advanced tool. About the main findings, these are the numbers. I can inform you that considering the CO2 savings, we are talking about something like 2,400 tons of CO2 reduction. We are doing the fine-tuning of these numbers, and these are the main economics findings of this feasibility study. We didn't perform yet the feasibility study using the Kelvin tool, but we think that during the next week you need to be aware that we are talking about we needed to update the technological setup of the different solutions, and we think that during next week we will close this analysis. Okay, I would like to thank you for your attention.
Thank you very much, Pedro. Next, we have Pablo Fernandez, energy efficiency engineer at Eleucon, and soWhat's responsible for the Spanish demo sites.
So good afternoon, everybody. My name is Pablo Fernandez. I work in a company called Eleucon. Regarding the soWhat project, we belong to the Spanish cluster, and we are in charge of the Spanish demo site of the project. That was the presentation, sorry. The Spanish demo site of the project is a pulp mill that belongs to ENCE company. ENCE company has 2 different business models. It is based on one side on the pulp plants, and on the other side on power energy plants that use biomass as fuel. You can see in the presentation that ENCE has 2 pulp plants in Spain, placed both in the northwest of Spain, and has also 6 power plants, I would say, in the south of Spain. You can see also the power capacity of the plants. If we take into account the total capacity of ENCE in Spain, it's 378 megawatts. Regarding the Spanish demo site, it's one of the pulp mills that ENCE has in Spain. Concretely, the one that is in the north region of Asturias. Most concretely near the Navia city, which is a small city. You can see in the picture an overview of the plant, and if you go to the top of the picture, you can see the Navia city. It's very close to the factory, more or less around 2 kilometers far away of the factory. At the beginning of the project, Eleucon developed an analysis of the processes of the plant, looking for potential scenarios of waste heat recovery. The results of the analysis were 3 scenarios. One of them, the biomass dryer, was built during 2019, the same years as the beginning of the soWhat project. This was important for us because we have had the possibility to gather data before and after the implementation of the biomass dryer. The second one, the lime kilns, is based in the waste heat recovery of the gases of the lime kilns. And the third one, the cooling towers, it's based in the construction of a district heating network that connects the factory to Navia city. Here we have the biomass dryer. You can see 2 photos of the facility and also a flow diagram of the facility in a simplified way. Regarding this diagram is divided into 2 parts. The one at the top is the bleaching stage, where the heat is recovered, and the other one is the biomass dryer. The working fluids are on one side the dilution of the bleaching stage, which is the hot fluid, and the cold fluid used into the biomass dryer is water. These 2 areas are connected through a plate heat exchanger. To give you an overview of the size of these exchangers, the plates are around 2 square meters of surface. This heat exchanger is completely sensored. It has sensors of temperature, pressure, and flow for both streams. And when the heat is the temperature of the heat stream is more or less 80 degrees. And with this temperature, we were able to increase the water used in the biomass dryer to 70 degrees, more or less. This water is used through several gas water heat exchangers that, using fans, are able to create a heat of hot air. There are 2 critical points in this facility. One is that the dilution contains fibers, so you can see that there is a fiber saver, that in other words it's a filter that is used in order to not introduce fibers into the heat exchanger. The other critical point is that you have to achieve a continuous surface of biomass introduced into the biomass boiler along the conveyor belt, in order to not have spaces without biomass along the conveyor, because if not, the air will cross these spaces and not the biomass, and you will not achieve a perfect drying of the biomass. So the final goal of this facility is to dry the biomass in order to increase the calorific power, the calorific value of the biomass, and save biomass through this solution. Here we have 2 screenshots of the introduction of this facility into the soWhat tool. The one on the left, you can see 2 blocks that represents on one side the biomass dryer and on the other side the bleaching stage. And the picture of the right-hand side, you can see that I would say that the system seems to be a bit more not too very complex, but there are a lot of data that we have gathered and introduced into this system. That was because the biomass dryer was built in 2019, and the beginning of the biomass dryer, the operation was difficult and it was not very stable. So we had to choose a resolution time for the data of 1 minute in order to have a good cleaning of the data before introducing it into the soWhat tool. Here we have the second scenario. You can see in the right-hand side that there is the same flow diagram than that I have showed you before, but in a more simplified way. And the idea is to use the hot exhaust that is generated into the lime kilns, which temperature is more or less 300 degrees. This is the highest temperature that has a stream in the factory, and use it after the heat exchanger of the biomass dryer in order to be able to increase the capacity of the biomass dryer. The main positive things are this high temperature, and also the increases of the capacity of the biomass dryer, because we have to take into account that not the total biomass consumption is dried now, more or less is the 30%. The main negative aspects are the distance between the line kilns and the biomass dryer that are opposite in the factory, so the piping is going to be very expensive. And the other negative aspect is that regarding the content of the gases, the price of the heat exchanger, that is a gas water heat exchanger, is going to be very, very expensive because of the materials. The third one is I have called it the cooling towers. This is the effluent treatment stage, a small part of it after the DAF system and the encounters. There's a need of cooling the effluent in this part of the system. So right now we are using cooling towers, but the idea is to connect this to the Navia city, to the public Navia city, and use it to cool the flow. The positive aspects are that the consumption of the cooling tower will be reduced, and the other thing is that the Navia city, as I have said to you before, is very close to the company. The main negative aspects is that when the idea was presented to the city council, was not very. They didn't show very much interest. That's because of the second main negative aspect, is that the surroundings of the factory are environmental protected areas, and taking the permissions to build a district heating that cross this area would be very, very hard. That's all from my side. Thank you very much, and I would be glad to answer any question. Thank you.
Thank you very much. Thank you very much, Pablo. And the last speaker of the day is Mr. Oliver Milling, Principal Researchers at Materials Processing Institute, and soWhat's responsible for the UK demo sites. The clicker is here.
Thank you. So I'm going to just start off this afternoon by explaining who we are, the Materials Processing Institute, our campus, our processes, about how we evaluated our waste heat, how we used the soWhat tool to simulate how we could best use it, and modeling of the scenarios, and finally the economics of the scenarios we modeled. So the Materials Processing Institute is a research and technology organisation in the northeast of England, and we're a centre for development and commercialisation of technology in materials, industrial decarbonisation and the circular economy. So our role in this project has been both doing some energy research and also as a demonstration cluster. So this is a picture of our campus. Our key energy users is we have a 5-ton pilot electric arc furnace, a ladle arc furnace and a continuous casting machine. And we also have a large amount of office and laboratory space. And our buildings, or our office buildings, are conveniently, they're named by colour, red, green and blue buildings. This is a picture of our process where we have an arc furnace for melting steel, and then we can cast it through a continuous casting machine. And now the cooling water from all our processes is just recirculated through a large water tank which contains over 80 cubic meters of water. And so when the furnaces are used at the caster, the temperature of the water increases. And so we identified that we could use that tank as a potential new source of waste heat, as sort of using it as an impromptu thermal store. So there's a large amount of data collection and aggregation at the early stages of the project. There's actually been parallel projects with this going on where all our process data is now pulled into a central data warehouse, and this project's been one of the early users of this data. It was also highlighted in the assessment of our data that we needed improved cooling water data, and that's now been implemented. Again, it was a parallel project. We had a new control system for the furnace that has much better energy monitoring and cooling water monitoring. But we still had the problem with the cooling water temperature. We didn't know, because the cooling water tank is in an outbuilding a little way away. So we actually installed quite a novel wireless system into that building, then transmits the data back to our network and puts it in the central data warehouse, so we can put it in parallel with all our other data. And this is one of the plots you get from our cooling tank, and you can see that roughly once a week we use the furnace, and the temperature in the water increases by relatively small amounts, 10, 12 degrees. But each melt, we're putting about 540 kilowatt hours of available added heat in that water. So when we work out how much heat that's available per year, that's about 21 megawatt hours of waste heat. We're also planning, we've got significant production increases in the next couple of years, so we'll probably be doubling the amount of times we use the furnace, so doubling the amount of available waste heat. So with the soWhat tool, we modeled our buildings on site. The main ones of interest are the green building, which is the one on the right of the picture, and the blue building on the left. The one in the center, which we call the red building, is heated by air source heat pumps, so there wasn't much ability to use waste heat in that building easily. But the tool enabled a very fast creation of those models, and then we can import the production data into that, and we can use, so we can then match the production data with the building heating data. So this is the output from the heating data. The plots behind actually comes from the tool, and then what I've done is I've just pulled that data out so that I could compare it with our gas consumption. So that's just showing the average daily gas consumption by month per year. And the error bars show that it models there's a higher and lower consumption on different days, partly because on a Monday morning, when the heating's been off for the weekend, you need more heat to get the building up to temperature, and some days it's just colder than others, so you get that variation. When we compared that to our gas use data, the estimates for the green building show that it's within about 12% of the heat we use, which is actually within the yearly variation of that data, so it's a good estimate. The blue building, the estimate of the heat we needed, was significantly less than the amount of gas we used, about 60% less. So to try and understand that, I talked to the engineers who maintain the building, and they said, oh yeah, the boilers in that building, very old, very inefficient, due for replacement. So that sounds about, they do use 1.5 times the gas of the other building. So then we use the tool to create a little heat network, modeling how we take the energy out of the thermal store into a heat pump into the heating system. And finally, we put it through the financial model, looked at the payback with the current production cycle and the planned production cycle. So the tool enables us to do very rapid and surprisingly accurate modeling of building heat demand, and that's compared very well to the measured data. The model's shown how we can implement taking the waste heat out of our cooling water, and that we should be able to use about 21 megawatt hours of waste heat per year. Although the payback is relatively slow, it's about 25 years, but as an industrial demonstration site, that may still be worthwhile for demonstrating that you can actually do this for larger industry. But the CO2 savings for even our small site is about 4 tons of CO2 a year, and that's because you're displacing each unit of natural gas with about 1 unit of electricity into a heat pump. If our production increases, double our production, the payback will be much shorter, about 12 years, and double the CO2 savings. So that's all from me. So, anyone got any questions, please ask.
Okay, thank you very much, Oliver. And for wrap-up and conclusions, we have with us Ariana Amati.
Thank you very much. I'm Marietta Amati. I work in Ruina Consulting, and I was the project coordinator for soWhat project. So before to conclude, I would like to say thank you very much for Eden, the University of Constanza, for having hosted us, and also to Sustainable Innovation for having organized this event. Basically, thank you very much to the whole consortium. Today we had the chance to present basically our results achieved during these three years and a half. soWhat is ending, and today we presented a lot of work and a good opportunity, considering that waste heat and cold is a significant opportunity in order to reduce, to improve efficiency and to reduce the greenhouse gas emission. So I guess that we can state that soWhat is a building block in order to increase the opportunity for waste heat and cold. As the scientific coordinator, mentioned today, there is no any similar tool on the market, so it's a very good opportunity. This project was performed also thanks to the whole consortium. As you can see today from the presentation, the consortium is very industry-oriented consortium, and we have the chance to collect a lot of feedback during the tool development from different kind of industries located in different geographical area during the within the Europe. Moreover, I would like also to thank the Alliance for Energy Cooperation in Europe, European industry, because during these 3 years and a half, we have the chance to exchange a lot of information with within other research and development projects. So thank you very much to everybody, and I hope to see you again and to collaborate in the future again. Thank you.
Thank you all. I guess we finished in time. Both the theologians will be happy. Thank you.